Okay. Up on YouTube too. Okay. So. What is that, Eldritch? Tried to hack into Twitch. Delete everything including OS. Oh, okay. It's a good command right there. So I've been interested in trying to relearn how to code, and the very end of chapter 3 in the E&M book has what looks to be a coding problem in it. I guess I think it is. I didn't actually confirm they said to write code, but I assume that this is coding. They don't actually say to code it, which is kind of funny, but this one says to write a program. Oh, maybe they want you to do 76 by hand, and then 77 with code. I might do them both with code, or I don't know. But they say that 76 says the answers, or it's based on the result of exercise 3.75, and I'm kind of trying 3.75 as well, so I might look at 3.75, and this one isn't really a coding one, but just see what it's like. So you can delete your Windows and get better performance in games? True. Windows is always using so much CPU. Why not just make it stop using all that CPU? If phi satisfies Laplace's equation, the average of these 6 values equal to x naught, y naught, z naught through terms. What? I don't understand what this means. I assume that's phi of x naught, y naught, z naught through terms of the third order in delta. You're gonna sleep? No worries for me except for good night and sleep well. Thanks for saying hi. And magnetism, so corrections. There's a little webpage with corrections. And I'm curious if this is on it. It's not on here. What page is it? 174? No? Okay. I was hoping to like confirm that that's definitely a typo. I assume it has to be a typo. It doesn't make sense for an average of 6 scalars to be equal to a point in the Taylor series of a point, I think. Um, but I assume we just kind of want the general formula for a Taylor series here. Hey, Alvito, how's it going? Yeah, so from n equals 0 to infinity of the nth derivative of a times x minus a over n factorial. So let's just, I mean, they give us 6 different things to make a Taylor series expansion for. Well, let's at least write it out for the first one here, and then maybe we can imagine the rest of them, because I imagine they're going to be very similar. This is going to be partial derivatives. So I'm going to write it a little bit differently from how Paul gives it, because that's for a single variable. Other than that, I would think that we can apply the exact same logic here. What am I doing? Taylor series expansion for phi at each of the 6 points. So wait a second. Okay, so we have a Taylor series centered at this is a okay, wait. We have a general function phi of x, y, z, and we assume it's representable by a Taylor series. That doesn't quite make sense though, because I haven't done a Taylor series for a multivariable function before, but they're only changing one variable at a time here, so I think it's basically going to be a single variable thing. I'm just trying to figure out how to actually write it in a way that makes sense. And the little difference here is we need a partial derivative here. And we're centered at x naught, y naught, z naught over, oh wait, we need, that's weird. We get x naught minus x naught plus delta to the n. So we just end up with delta to the n in there, minus delta to the n. Which, that's probably the point. I wish I gave myself some more room. Let me start more over here. Let's look at minus delta. I don't need that n in parentheses. Ah. So that bit is just delta to the n. This bit is minus delta to the n. I wonder if that's going to give us some neat trick. I'm not going to write out for the other 4 because they're really going to be the same thing. symmetrically surround the point x naught, y naught, z naught at a distance delta. Show that if Laplace, or if phi satisfies Laplace's equation, which is if the Laplacian of phi equals 0, and the Laplacian of phi, since we're working in Cartesian coordinates, is I believe this. Wait, no, oh my god, dude. This... I hate the higher order derivative notation with Leibniz. I know how it works and why it works. I just, it doesn't like come to me naturally still though. Oops. The average of these 6 values. Oh! Zach! Thank you. Hey everyone, welcome in. Hey Peach Tea. How's your stream? Nothing much. But just started things up. I was, you know, just doing some problems to fill in the time. And I noticed in the E&M book, there was a neat little coding problem. And I was working on 75 first, which is like maybe some of the lead up to the actual coding problem. Hey, SPQ. The actual kind of coding involved, I think, is going to be for 76 and 77. Called the relaxation method, which I don't imagine I'm going to feel very relaxed as I'm working on it, but hey, Dr. Cook. Oh, hey, this is Purcell right here, since you were curious. I'll let someone ask the question. I'm going to switch away from it, but Phobos, hey. Oh, Phobos, I have to say, that, yeah, I was looking at your code for, on your GitHub for the, electric field point charge thing that I can't find the words for it, apparently. And, because I was trying, just as a little practice last night, I was trying to make a vector field, for 2 positive point charges. And I was having issues with it, so I was looking at how you did it, and you did it in a way smarter way than I did, which I'm not surprised by. I stole your work for like the little bit with epsilon, and also like some of your calculations, because the first way I did it was terrible. But you're smart. You are. It's a one-liner in Mathematica. Oh, the thing on the screen. It probably is, but... Or do you mean the vector field for like 2 positive point charges? I don't know, but either way, I want to... plotting the vector field. Oh, okay. I'm sure I could have compressed this a bit, but I found out because I didn't know that Quiver. I guess it's maybe a library that works in a few languages. I use Quiver with MATLAB, and apparently it exists in Python as well. And I assume it's like a neat pun with like how a bunch of arrows make up a vector field, and you have a bunch of arrows in a quiver. But anyway, this is just 2 positive pointers on the x-axis. They're equidistant from the origin. And I get something that nearly makes sense, but is but doesn't. And you don't have to like troubleshoot my code for me if you don't want. I'm just like sharing because I thought this was fun. I get these things pretty close to the point charge, uh, depending on how, like I was messing around with the code a little bit. They go to like 60,000 or something ridiculous that they definitely shouldn't be going to, and it's messing up the scale. I feel like most of the other vectors are they seem reasonable in how they're pointing in their relative magnitudes, but I cannot for the life of me figure out why these ones that are so close shoot up some seemingly unreasonably or unrealistically high magnitudes. So that's what I was working on last night, and then I rage quit. But I might work on it more on stream or something. Some advanced visualization method for matplotlib. Pretty nice. Draw the flow lines better. Ooh, okay. But yeah, I really like. I don't know. I just think vector fields are kind of cool in general to see. Yeah, Dr. Cook, but there was still like I put in I stole a little failsafe from Phobos, where if it was like I mean, even if I bumped up this failsafe, I put it to like 1 or something at some point too, just to try and force it to be at least a distance of 1 away. Oh, you know, I even just arbitrarily made k equal to 1 as well. Like I was trying to force it to be on a, or sorry, this idea with the epsilon is that if you get too close to the point charge, just if you're less than 10 times 10 to negative 10 distance from the point charge, then just set it to that distance so you're not dividing by too small of a number. But some advanced visual. Yeah, I already read that. The electric field strength. Yeah, I feel like it shouldn't be. I thought it was enough distance away that it wouldn't. It's still like half a unit away, like to the right and up. I think, so which makes me think it's not that close. Stream plot, something I don't recall my example is. You live next to the other E&M stuff. Can always clamp the vector to some maximum that makes sense. Yeah, I guess we have to do something like this, but again with on U and V. But I don't know exactly how to accomplish that, I guess. I don't know, it probably worth some more thinking. It's gone real bad, now I'm getting ads in Spanish, me no habla español. I think I got some ads in Spanish too. Twitch shows me the same ads over and over again, and it gets really annoying. Like, I'm never in my life going to watch Those About to Die, because I've seen the same exact 30-second ad a million times. For hair care instead of the army? Okay. But yeah, I don't know. So that's what I was working on last night. I want to look more if the values I'm actually getting are reasonable. Because it might, like Dr. Cook said, it might just be correct that they're that giant. I still like to take them out in some way because they're messing up the scale, but I want to figure out if they're reasonable, and if they're not reasonable, how do I fix it? But I'm not all that interested in it. I mean, I can, but I was getting distracted by this very long numerical methods problem in the Purcell book. They know how much hair I don't have. They know their effort is doubly wasted. Ugh. My hair is on the way out. Like, the length of it covers it, and my widow's peak covers it, but like right along here, my hairline is receding. It's not good. It has been receding for a long time, like slowly. Is the magnitude of E closer E 4 times greater? Okay. I guess I should make it actually print out the values. Oh, that's gonna be a ton of data. Can I make it print out the... I don't know how the vectors actually look. Yeah, I guess I don't know which indices to check, though, if I do that. If I have it's a mesh grid. I don't know why I made this variable name so freaking long, but it's a mesh grid. It has 20 steps, I guess. So that'd be 400 points total, but I guess we only need to care it's 20 by 20. Your watch streak is now quartic. What's a perfect fourth power that's around your streak? What's 4 to the fourth? That's 2. Well, oh, 3 to the fourth? 81? There we go, yeah. I worked it out. I'll just arbitrarily print you and see how much it yells at me. Let's turn one charge off. Well, part of the stupid way that I coded this is like Hobos made either a function or a class for each point charge. I think it was a function. Like individually, I just did the calculations for both of them at the same time. I probably could split them up, but where... I'm just curious where in this array these giant values are happening. I don't see them. These are all negative exponents. I may need to look at the y values. What? I don't see it here either. Where are the vectors that are so giant coming from? These are all less than 1. I'll just multiply by 10 to the 6. True. Where did I... Oh, wait. They're actually... If I comment that out, and I comment that out, I might actually just be good. This should get it, I think, just for the single charge at the positive. Okay, so I'm still getting the same exact behavior, just it's basically what it's basically the same exact thing, but cut it in half. Oops. I can bring it up in Paint. But like, it's kind of weird that I'm not actually seeing these gigantic values actually in U and V. Actually, I just remembered I can do Oh no, I can't do that. I forgot that doesn't work. Ah, okay. Never mind. Numerically check that having the distance multiplies the field strength by 4. I want to try one other thing. U x v dot x. That's so weird. Those are small numbers. They like, I don't know. Like, this is most certainly not the biggest vector that's being drawn. Color/opacity to indicate field strength. Do the vectors get drawn to the grid scale? I have no clue. I don't know how any of this actually works. Oh, it could be the relative scale. I guess you're right. Yeah. That's so weird that they would shoot up like 100,000, I guess, but... Oh, of course it goes to the negatives. I want like the absolute values. I'm not gonna bother trying to figure that out. So... Oh, okay. Thank you. U.abs. Min. Just to get a, like, the relative scales that we're working with, I guess. Nar. Oh, np.abs of that thing. I can't read. It's a problem. Okay, so it's 4. Oh, okay, so I guess that does make sense then. We have 4 orders of magnitude, I guess, the difference. Okay. So if we took I wanted to, so, like, I saw you can do like this sort of thing with numpy. It's great. If it's greater than or equal to like 10 to the -1, like we take all of those elements and just knock them down by an order of magnitude. Would that do what we wanted? Like, I want to do something like this and like plot that. Maybe. It's not going to be, it's no longer like going to be accurate, but yeah, I mean, it's okay, you're right, Dr. Pig. It's probably better to have unit vectors showing direction, and then separately a heat map like Phobos has done. You like the chaos? Oh, wait. I mean, if we do it by the same... I was gonna, like... If you scale it by the same value, we preserve length, right? But yeah, you're probably... It's probably better to have a vector field where everything is equal and then a heat map. And Phobos made those heat maps before. I was... You know, use a log scale. Oh, that's probably better. If I'm gonna do it in this obtuse way that I insist on doing it. I assume we have like log. Do log 10. U log, V log. Ooh, that's not right. I feel like I made art though. Bring this up. I don't know why I keep closing out of paint. This feels very, like, minimal, yet very meaningful. Not actually meaningful physically, just, you know. This represents something. I don't know. Anyway, oh, because there's negative values, duh. Yeah, that's kind of a problem. We would need to take the absolute value, but then slap another negative in front of all the ones that were negative if we wanted to make this log approach work. Log square root u squared plus v squared. Okay, so I want to take u. Am I dividing u by that thing you just put? Well, no, I mean, that'll just make it a u. We could just look at the unit vectors, I guess, if we wanted to go that way. I don't know if, would the log change much there? Okay. So this is actually, I think this is what, you know, this is probably a better depiction of what I was going for with this, of actually seeing the direction of things. I wonder if I could superimpose a heat map onto this, like on the same thing. Or color the arrows according... I bet you could. I need to look up how matplotlib works, though. No, it makes sense to me, at least. Price is lower than any competitor? Okay, there have been about 1 million like people have claimed the exact same thing. I guess maybe you're all speaking for streamers though. Goodbye. You are the weakest link. Most difficult problems copied from SO will be the Project Euler section. Oh, from Stack Overflow? I did just miss a golden opportunity. That was my big break right there. That's a good question. Like, what are the hardest problems on Stack Overflow? For like math, there's Math Overflow, which is where like the super niche like doctorate level math happens. And I've never even like slightly heard of any of the words that they're using. Don't access my location, Google. Yeah, I feel like we can just put them both onto the same plot. Coloring the arrows or making them opaque would look better. I mean, that would be more relevant because you would have spots on the heat map where that like don't have an arrow with them. I wonder, like, does Quiver give you the option to color the arrows like that though? Python Quiver. Quargs. Mathematica. Oh god. If you're an n-dimensional generalized matrix, you might have to copy that. Oh, there's scale parameters that could have probably fixed this issue too. Angles? Me. Scales the length of the arrow inversely. Oh, list color. Oh, we'd have to make a list of all the colors though? I bet there's a way to do that. We'd have to calculate a new list. I don't know, how would we like... So we could make a tuple of RGB values. I assume they range from like 0 to 255? Oh no, they're on 0 to 1. So we could definitely make a scaling where like, this is annoying. I wish it would do this for me. I think we'd have to make an array of the same size that stores these like tuples here for each point. Doing colors is always annoying. Yeah, I know how to spell. Okay, so holy. Get rid of the grid if we're going to do well, actually, we can keep the grid. Why not? Like if we wanted to transition from like say red to blue, maybe red is the biggest magnitude, blue is the lowest. We need to figure out the minimum and the maximum for each magnitude. Now, do I want max or maximum? Just assume I want max. No. Sigmoid? I've never heard of that in my life. Oh. That seems nice. Well, but what if I wanted to do it for me? Python. Like I don't want to actually think here. Hey, syntax. Arctan is fun too. Oh, I guess that would do the trick. But like, it's more of a feeling. But like, I guess I would plug in the magnitudes here for x. Which, yeah, okay. Let's see how that works. Where am I going? Hmm. 1 plus e to the minus x. That thing from Animal Crossing outside. Oh, I never played Animal Crossing. So, okay, I guess that, well, wait. No, I'm trying to get this into tuples, aren't they? It assigns it between 0 and 1. That's still helpful. I think. Red, green, blue. So if I want red to be the biggest, Then I can just take scaled magnitudes, 0 for green, and then 1 minus scaled magnitudes for blue. And I need to do it up here. But well, let's see if this does anything magical. Besides crash. Come on. Oh wait, I need to close out of that. Oh. That's not good. I feel like I'm being yelled at with all these error messages. Is this actually how you would make... Oh wait, this is a tuple of arrays. I need an array of tuples. How the hell does that work? Yeah, this is all wrong. The scaled magnitudes aren't quite correct. Well, I believe that. Colors equals... Like, really? Literally with a 4? That does it? Or, well, I guess I need to change the ABC? Yeah, so I guess I realized I'm only plugging in positive values up here. If the magnitude is very big, it'll be very close to 1, which is what I want, right? And if it's very small, it'll be close to a half. Oh. Because e to the 0 is 1. That's annoying. How does that work? That's not how the function looks. Oh, yes it is. Oh, yeah, Ben, I think you showed me that. It was some crazy, like, integral thing, wasn't it? Someone showed me that. I never remember seeing that. Hey, I don't even know how to say that. Algebraic geometry, no, I can't do that, unfortunately. Maybe there's someone around who knows it, but I do not know the first, I don't know the first thing about algebraic geometry. So yeah, the scale is definitely wrong. If I want it to be between 0... I mean, I guess we could just keep it between 1 and 1/2, right? Two times sigmoid. Okay, let's do that. Well, let's just change that to a 2. It's just intro. I have a bachelor's. I that's algebraic geometry is like grad school stuff, isn't it? Yeah, sure, critical. Ugh. What is it not like now? All right, let's see what critical posted. Hey, SJ, DJ, SJ. Favorite professor? Oh, no. I mean, there's people on Twitch who are better qualified than I am. I don't know of anyone who knows algebraic geometry specifically. But there are other math streamers out there. I can't recommend any of them in particular that can help you, though. And Dr. Cook's been streaming as well. But yeah, if you're doing algebraic geometry, I can't point you in a specific direction. I'm sorry. Okay, I never took proof-based linear algebra, so critically, I just want to know what this means. A subspace of vector v is a subset H of v that has 3 properties. The 0 vector of v is an H. Okay, so I think the best thing to do is to show an example for R3. So like, I guess before I get into it though, critical, like, do you want to know like what a subspace actually is, or are you asking about a property that's listed down here? Okay, so ignore the stuff up top here. So let's say we're thinking about R3, and the vectors that we're thinking about are, say, 1, 0, 1, 0, 1, 0. Was that a bad choice of vectors? No, it's not. I don't think so, at least. -1, 2, in 0? Do we have a... Oh, no, that's bad, that's bad. 3, I think we'll fix this up. Yeah, I hope so. So let me actually plug this into Wolfram. I want to choose 3. I'm trying to make up an example with 3 linearly independent vectors, so they do span all of R3. And I want to make sure I'm choosing a good example. And I don't want to choose like the simple thing necessarily. Okay, non-zero determined. I think it means we're good. Yeah. Okay, so what I just checked in Wolfram Alpha is that these 3 vectors are indeed linearly independent, so they do span all of R3. So remember that R3 means the XYZ plane, or not plane, but space, because you know obviously it's more like a cube than a plane. So we can go anywhere we want in here. It's gonna be hard to actually draw. Basically, the the idea is they span all of R3 there. But we could take a subspace of these vectors. Let's just choose the first two. Any two will work, even one would work, but let's just choose two. We could take a subspace of these three vectors that span R3 and look at where these things span, I think is the point. So these still exist in R3. But they're not going to span all of R3. So, oh man, 101 is like pointing diagonally like, no, it's not. It's going out like that, I guess. And then we also have something 010 going right up the, man, I could have chosen an example that'd be easier to draw here. But the idea is rather than spanning all of R3, we only span a plane inside of R3 that is going to be super annoying to draw with the vectors that I chose in particular. But I kind of think of it as these three vectors almost make a cube with where all you can go with their span. Like, it's just, I guess like a cube, but it's infinitely big, so you can go anywhere in R3 you want. Whereas these two vectors reduce from a cube down into just like a plane, like just one sheet. And that's because of the idea of linear combinations. You can take these vectors, add them together, multiply them by whatever number you want. And if you do that for every single possible combination, you get a plane like this. But if you do it up here, you get an actual like cube. And I think about it very geometrically like that. That's the idea of what a subspace is, as far as I remember. And they're giving you the fancier explanation. If the determinant is non-zero, it does span all of the space. Yeah. I was using a little trick there, because there's a ton of different ways to check that. And checking determinant was 0 was just the quickest one that I had quickly available. Why is that being weird? Oh, I see why it's being weird. And so what they're saying here is the more formal version of what I was trying to explain, where if it's closed under addition, it means you have to have every possible combination that you can get of those by adding the two vectors together. And that's what a linear combination is, in part. The other part is that you can multiply by a scalar, and if it just goes under scalars, it has to include every multiple of each of those vectors. And every multiple added together. So it's really still this idea of like linear combinations and where do they span. The kind of, I think, simple explanation is that if they give you a set of vectors, you can choose any combination of those vectors you want, as long as you take at least one out. And that is and every linear combination of those vectors is your subspace. So you could also, with these vectors that I chose, instead of choosing that for a subspace, I could have chosen just one of them, 0, 1, 0. And instead of we went from a cube to a plane, and now we're going to go from a plane to a line, or, a cube to a line, I guess. Zero, one, oh my god, dude. I forgot how 0... I can't believe I did that. 0, 1, 0 is on the y-axis. Oh my god. In my head, I switched the y and z coordinates for both of these. 1, 0, 1 is up there, and 0, 1, 0 is down there. It's still not easy to draw, but yeah, that's not even the right perspective, but I'm just gonna leave it like that. The actual drawing itself, the concept is still right, going from a cube to a plane. I drew the plane slightly wrong, but if you go down to 0, 1, 0, that's 0, 1, 0 goes along the y-axis, and we want to take any, there's no addition really to do here, but for the scalar multiplication part, you can make it as long or as short as you want, so it's anywhere on the y-axis you want, including the negatives. So that's just a line rather than a plane. Yeah, if you got 3 vectors, you can do 2, you can do 1. As long as you take one of them out and you allow for any scalar multiple and any addition with those vectors, you have a subspace. And they're saying that this subspace is a vector space still, in its own right. It's not going to span the entire thing that the original set did, but it's still a vector space and has all the properties that a normal vector space has. So in each of my examples, we can't name a subspace that spans all of our 3 because we do have to take one of those vectors out. But everything that I put there are vector spaces in their own right. The second system, I guess you're even allowed to take just the 0 vector because the 0 vector is in every vector space, I think. Recall that the term linear combination refers to any sum. Yeah, so I think I covered the stuff that's on here, but if you still have a question, then let me know. Okay. W be the union of the first and third quadrants in the xy plane. Okay. If U is in W and C is any scalar, is CU in W? Why? Ah. Let's make a drawing. Okay, so they're saying they have a vector space that is just the first quadrant and the third quadrant. So we're allowed to draw any vector we want in these quadrants, and they're kind of challenging you to see if you can somehow break the idea that this is a subspace of R2. And the two properties that we really have to play with are scalar multiples and additions. So the first thing they ask is a scalar multiple. So draw any vector you want. Let's say this is 2, 1. And take any scalar multiple of this vector you want. And the challenge is to try to end up in the second or the fourth quadrants because we want to try and disprove this thing. I think the idea here is that I don't see a way to do a scalar multiple of this vector to break out of the first and third quadrants. Like, going shorter doesn't help. Going farther doesn't help. Reversing the direction doesn't help. So I think if you can name any vector you want in the first or third quadrant here, but using only scalar multiples, I don't think there's a way. I think this is consistent for the scalar multiple part bit. I can't find a way to get into the second or fourth quadrants just using scalar multiples. The second part of the question, hey Fembox. Oh, that's a neat example. I'm gonna go with a different example because it was more natural for me to see it. But you're right, that would also work. The second part of the question, they kind of spoiled the answer that you should get, but that's a nice thing, which is use addition to show that you can actually get into the second or the fourth quadrant. So if I were to do this, with drawings again, let's say I have a vector, let's take 2, 1 again. And then let's take like -1, let's call it -4 or something. And let's add these two things together. Wait, I didn't do that right. No, I did. Let me do it off to the side here. 2, 1 plus -1 minus 4. It's going to be 1, -3, right? So 1, -3, we go 1 to the right and down 3. Uh-oh. We're in the fourth quadrant here. This thing is not closed under addition because we're only defining the first and third quadrants, and we just broke out of that. So that's enough to disprove it. Fembox found a bit of a craftier one, which is a little bit more elegant. I didn't see it at first, though, which is why I wanted to show like this example, because I think it's a little like, it was easier for me to see at least. But Fembox noticed that by the definition they gave, greater than or equal to 0, that W does include, I guess, I want to call them the unit vectors, but that's not a good term for them. This vector here is included because x times y is equal to 0, so it is in W. And also this vector here because xy is equal to 0 there. You can add these up to get 1, -1. And 1, -1 is just also in the fourth quadrant. But that right there has disproved it. A vector space has to have both at the same time, both scalar multiplication and addition. So yeah, we tried scalar at first. We couldn't break it like that, so then we went to addition. Yeah, I guess you would call those closure properties. So you could technically, like, basically using the properties B and C here. A, like, it's kind of like a, you probably wouldn't use that to, they're probably not going to ask you a question or praise you to use A. I see you posted a bunch more questions. Oh, the automod was catching these stupid messages, and now it's not. Okay. I'm not going to do all these for you critical, but I'll at least try and get you a start on them. What? For number 3, I don't even... What if V1 and V2 are the entire vector space? Really? Oh... Okay. I don't think so, critical. Were you all good with number 2? Okay. Well, I saw you posted a bunch more questions. Example 3, sure. I'm not going to do all these for you, though. I don't know how you'd write the proof for this. The idea is that the span of V1 and V2 is a constant times V1 plus a constant times V2. It's just back to that linear combination thing. And you'd have to show that that linear combination of V1 and V2 is closed under addition and multiplication by scalars, which I think I would just say that it is, but I don't think that's a proof. I don't actually know how you write out a proof for 3. I mean, if you want, you can send me the answer for number 3 and I can try and explain it to you, but I don't have anything, I don't know what to say about 3. Like, I don't know how you write that proof, I guess. Okay, well, for 4, the task is to basically go through these properties A, B, and C and show that it has all 3 of them. So the first one, the 0 vector of V is an H. Can you name a value for T that gives you the 0 vector here? Hey, Andrews. So critical, I guess I'm asking you, like, or I'm not sure if you're still thinking, but like, the first part of this question is just to find a value of T that gives you zeros in all 3 of these things. You lost your streak? Oh no. So what value of T would do that for you, critical? So we really just want to show that this thing includes all zeros, so T equals 0 is going to do that for us. Because you get 0, 0, and 0. That's all you have to do for the first part of this question to prove the property for A. Yeah. But do you understand like why we care about T equals 0? Like we need to prove each of these 3 properties here. And T equals 0 shows that it's true for A. If you want to prove that something is a subspace, then yeah. Yeah, exactly that. Like, we're trying to show this thing is a subspace of R3. So we go back to this definition and prove each of these 3 properties. So T equals 0 proves it for A. For B, we want to show that it's closed under vector addition, which is another thing where I don't know how to phrase it. We only have a single vector, so there's nothing really to add. I guess I would say that since H only contains a single vector, it's closed under addition or something. Hey, underscore. Oh, it's been a minute. can you use theorem 1? I don't see what initial like vector space we're given, I guess. Or oh wait. Oh, if you know this thing is a vector space, you would say that its span. Okay, like you would pull the T outside, and that is the span of something. Okay, let's do both explanations then. Yeah, actually, and I guess you can use that for example 5 as well. Okay, yeah, I didn't see that that would be helpful. All right, so critical, that I'll show you a second way to do this as well, but just to keep on with the train of thought that we were just on with proving these three properties. It's closed out under addition because you only have a single vector, so I don't think there's anything to add anyway. It's closed under multiplication by scalars because it's actually going to get into the idea of theorem 1, I guess. You could rewrite this vector 2t0 minus t as t times the vector 2, 0, minus 1. And so this is just a scalar times, this includes every scalar multiple of 2, 0, minus 1. So it's going to be closed under scalar multiplication. Like, if you multiply it by 2, it's still going to be in there. Or, you know, if you want to put any other scalar multiple you want in front, we can still... Actually, that's not... it's not necessarily a 2 going in front of there, but for any multiple of 2, 0, minus 1 you want, we can name a value of t that would get you that. So if someone said, oh, is there a multiple of t that would get you to 6, 0, minus 3? We'd say yes, we would take t equals to minus 3. And so that would, I mean, it's not really that good of a proof, but that's the idea of it. I don't know how you actually like write the proof part of this, like, or how formal it has to be. Well, the addition part I said, critical. It's we only have one vector. Like, there's nothing to add, so I will just say that since H only contains a single vector, it's closed under addition. Something like that, I guess. But the other idea that underscore mentioned is using theorem 1 here. Which is, we can notice that t times 2, 0, minus 1 is the span of of 2, 0, minus 1. Sorry, it's partially covered. Which means by theorem 1, Wait, I'm sorry. So, are in a vector space V. I'm trying to say it correctly. We have to show that this 2, 0, minus 1 vector are in a vector space V, which 2, 0, minus 1 is in a vector space R3, I think is how you would say it. Oh my god. Then the span of 2, 0, minus 1, which is really just every scalar multiple t times 2, 0, minus 1, is a subspace of R3. By theorem 1. Oh, that's how you would do it, Zach? Okay. It's kind of weird to me when there's only one vector involved. Yeah, so in theorem 1, oops. We just have a single V1 in this list. And that V1 is 2, 0, minus 1. And it's contained within a vector space. It's not the entire vector space, which Anders is pointing out. Like, it's inside of R3. It's not all of R3, but it is in R3 or some other three-dimensional vector space, I guess. It doesn't have to be R3. But we care about R3 in problem 4, or example 4, because they want to show the subspace of R3 specifically. That's why I said R3 when what I wrote on the board. And since we proved the first part of the if, the second part must be true. Example 5. Yeah, I think it's the same idea. With a slightly different why they call this a theorem, though. It's kind of small subspace of V. Yeah, I'm a little bit confused by it, 2 underscore. I just chalk it up to me not being good with linear algebra, though. Yeah, I think it's a good step to do critical. That's my thought for how we'd want to do this as well. S plus 3t. S minus t. 2s minus t, was it? And 4t, okay. So I would split this up into a sum of 2 vectors. Split it up based on the s's and the t's because it's possible here. So 1, 1, 2, 0. plus, that's like a t. Three minus 1 minus 1, 4. And once you have it in this form, you can make either argument you want, I think, using the three properties or using theorem 1. But probably defines the span by all combination of vectors in the set. To characterize the span in the way you said. Interesting. So yeah, in this problem, if you wanted to use theorem 1, you'd say the two vectors 1, 1, 2, 0, and 3, minus 1, minus 1, 4 are a vector space in R4, because that's what we want to prove something about, or prove a subspace of. So you would say the span of those two vectors is a subspace of R4, and that this vector they gave us here is just the span of those two vectors. So you can make the same exact argument there with theorem 1. Or you can go down the list here and prove each of these. Actually, the closed-ended addition part, I'm still not really sure how you prove that, even when you do have two vectors. Like, the thing that we have just already has this every possible sum of the two vectors, so I don't know what more there is to say, I guess. But yeah, that's the idea of R5. Do you say that you want to wrap it up with 5, or unless you have any questions about 5, but okay, no worries. Should believe that. Okay, so what was I doing before this? I think we're working on this. I was trying to figure out how this color map actually works. That's right, or the heat map. Wait. This doesn't look right. I don't know what this is. Unless I'm just not reading this output right. I want this to be an array of 3 tuples. I guess like a vector of 3 tuples. What does scaled magnitudes look like? Wait, okay, so this thing has... This is a two-dimensional vector. I guess that's actually right. Ah, okay, no, it... I'm still expecting each... Okay, so as my expectation for the output was wrong, but I still think I'm expecting each of these entries individually to be a 3-tuple, but this is like... It's not that. Oh, yeah. I was showing this at the start of the stream before Critical asked that question. I was kind of going off the deep end with it and doing all sorts of crazy things, which is where what I was trying to make work here. Oh, and yeah. Let me show you the crazier one. I would need to do that and that equals G. That's how it was. How it at the start of the stream. So last night I was working on this just for fun. It's the vector field for two positive point charges at an equal distance away from the origin. And I rage quit last night trying to deal with these giant vectors close to each charge. And making them not go out to like 600,000 like they were before, or like they still are. And Dr. Cook had a good suggestion, which is instead of trying to show both the direction and the magnitude at the same time, why not make them all unit vectors? Because it might actually, for some reason, or it might actually be proper that those vectors are so giant because there's like a difference of like 10,000 in the orders of magnitude between these vectors. So instead of trying to show the magnitude and direction at the same time, why not do unit vectors for all these and then do a heat map for magnitude, or like color the vectors according to their magnitude. Oops, what's that? What? Oh, I was clicked into OBS. And I think I saw, okay, yeah. So this is what happens after I did the same thing, but I made them all unit vectors instead. But now I want to color these arrows according to their magnitude. And that's been a little bit annoying. Because this clever function that actually makes the vector field, I think it needs a two-dimensional array of 3 tuples, and those 3 tuples have the RGB values from 0 to 1. So I'm putting the magnitudes into a sigmoid function that's a little bit scaled around to force it to be between 0 and 1. And then I want to take those scaled magnitudes and use them to transition the colors from red for the highest to blue for the lowest. But I can't actually seem to figure out how to make a two-dimensional array where each entry is a 3-tuple like this. This is nearly right, but not quite. And a couple of the ideas I stole from Phobos's GitHub, shamelessly. And then Dr. Cook and Phobos were in chat earlier for further helping out. Yeah. So I can see the scaling for myself. Okay, yeah. So the scaling is good that Dr. Cook suggested. I mean, could I accomplish the same thing with a hex string? We would have, I guess, like... I think I could. That'd be a lot more manual, though. I'd have to assign these continuous values to, like, discrete steps for each hex digit. And that sounds annoying. Let's just Python quiver color vector according to magnitude. So someone else surely has to have done this before, right? What? HSV to RGB? How does HSV work? Hue saturation value? Why would you convert the angle of the vector, though? If angle is less than 0, you take the angle... Oh, it's okay. First you take the angle... Okay, that's just if you don't have a... If you give it some weird angle. Why do they care about this? I don't know what hue does. I don't know how HSV actually works, but if we just do the same idea, I guess. Vector to RGB. Are they actually passing this into? C is np.array list map vector to RGB. Oh, really, Zach? Oh, wow, that's kind of crazy. Paul Klee meets Perry the Platypus? I don't know who Paul Klee is, but I can definitely see the Perry the Platypus vibes. Hmm. These are kind of cool. Ooh, the gamma function. That's the coolest one yet. Um, I kind of want to blindly copy Stack Exchange right now. That's apparently the mood that I'm in here. So this first one is going to be, man. Okay, I don't want to copy over their like angle code as well, but I'm gonna do that, I guess. We don't even we don't have the vectors as angle and magnitude. We have them as Cartesian coordinates. Ugh. Okay, you know what? I don't feel like doing this. I want to go back to the problem I was doing at the very start of stream. Which was this number 75, but leading into a numerical methods like question that seems to involve some coding. I feel like dealing with colors is not the most important thing to work on right now. Okay, so for 75, this is what I had written on the board, or what I still have written on the board. besides the span stuff at the bottom there, but if phi satisfies Laplace's equation, I should verify that I got Laplace's equation correct. The second order partials in each variable of phi equals 0 added together. Okay, the Laplacian of phi is 0, and the Laplacian of phi, it is that. Okay, good. Oops. And so I'm taking like this little bit here as a typo. I assume that's supposed to be phi of x naught, y naught, z naught. So I wasn't planning to write out all 6 of these Taylor series expansions because I think they're all going to look at the same as the first 2 things I have written there on the board. Just you switch up what you're doing the partial derivative of. And that's really the only difference, I guess, because the x naught, y naught, z naught cancel anyway. Through terms of the third order. Oh yeah, I still don't understand that theorem, Fembox. I read it a few times, like I don't get this, but I'm just gonna move on for now. And the coming back to a later part never came, I guess. Hey, within timelessness. You have an unrelated question about math. If you use 1 as half of 0? I assume you have more to type there, so I'll wait to see your entire question. 1 being half of 0 doesn't make sense to me, but there might be a typo, or you might still be getting your thought out there. So we're given that this bit here is true. And we want to show the average of these 6 values, and the 6 values being the various Taylor series, added together divided by 6, I guess. We need a lot of space here. Well, wait, can we combine these 2 in some way? Because they're near the same thing, just one is minus delta to the n, one is positive delta to the n. We can. If we had factored this bit out, And then we have times delta. Really? Oh, wait. Delta to the n plus minus delta to the n. So they don't necessarily cancel. For even powers of n, there's still... Yeah, because we have these two things summed together, and I factored out that bit and that bit. So we have a minus delta to the n plus... Okay, yeah, I think that's a bit of a shorthand for the first two things added, and we can mimic... That's a... Oh my god, dude. Don't even look at that sigma. Let's use the same format for the other two partials. Okay. So that's... Oh, wait. Over 6. Average. You guys need to make this less interesting content. Twitch is too addictive? Yeah. One Twitch except when I'm at work. Yeah. This is These streams are weirdly interesting. Yeah, that does make sense for what we're going to get here. So is the problem blocking? Not yet, but almost. Up to third order. So that's what I was just about to try to remember. The third order means that we go up to and including n equals 3. Oh, okay. So it's equal to 0 for odd n. To the 2k plus 1 plus minus delta to the 2k plus 1 equals 0. And for n equals 2, since the Laplacian equals 0. Okay. I like that. So that eliminates n equals 1, n equals 2, n equals 3. So you're right, I agree. All we have left over is n equals 0. Which means the partials, I guess, go away entirely. 0 factorial is 1. I'm just going to write phi. We know where we're evaluating phi at. Phi times this becomes 2, and that's what's going to get rid of the 6. Okay. Summed average is just the central value up to the third order. Okay. It's a nice little problem. Just a 1 star, and I feel like I feel like I got it as quickly as you should get a 1 star problem in theory. Unlike other times where we've gone off the deep end of doing some crazy integral that we didn't have to do. There's been multiple times. Oh, that's how it's connected to the theorem that Fembach said. Yeah, for a lot of the concepts and basically every theorem the book has shown so far, I feel like my understanding of it is pretty tenuous. It's like this explanation here, the book's explanation made no sense to me. This is one of the parts of the book that I felt was awkwardly phrased, at least for me, who hasn't learned this before. Oh, okay. And so the thing that we just did on the board with the Laplacian is only really applicable to really small spheres, but the theorem is applicable to any sphere. According to the rotational symmetry of the Laplace equation. That's what Dr. Cook is saying. Oh, wait! This theorem is saying that you do the same amount of work if you have a positive point charge. It takes the same amount of work to bring a second positive point charge right to the center of that first one, as it would to shrink a sphere from infinity to a given radius. Is that what the theorem is saying? Instead of bringing 1 point charge a long way, you can bring an entire sphere a little bit of a way, I guess, is how I think I got that now. King over infinity. Six symmetric points, each of them gives 6. Averaging everything to the group of 6, so you get the same result. Not sure I followed that. I mean, it probably... I'm just trying to figure out what theorem 2.1 is even saying in the first place, not trying to prove it. Is it saying that it would take... my interpretation of theorem 2.1 is that you have your point charge that's positive q, and you bring a second, positive test charge q prime all the way to q, ignoring combining the two charges, I guess. There's a sphere or like this would take the same amount of work as it would to shrink as like, you know, some kind of giant sphere that's initially out here down to some smaller radius here. That's how I'm interpreting that, where like you can relate the shrinking of a sphere to bring in a single positive test charge. No. Yeah, the thing about the Laplacian is, I guess not really. I was talking only about like theorem 2.1 of the book lists here. Forgetting temporarily about the Laplacian, because I've read this part of the book a couple times and I still don't know what this actually means, unless I just figured it out with what I said on the board. Or maybe it's not even saying that. I don't know. I might just invented my own stupid theorem. That's not true. I never what it even means to satisfy Laplace's equation. Like, yeah, I forgot, like, chapter 2 is really math intense, and I forgot a lot of the interpretation of what the Laplacian actually even means. But I don't know, it's not that important to get to right now, because I do want to keep working on that chapter 3 problem. The divergence of the gradient, yeah. I don't know. What? Never mind, okay. I know, I need to go back and reread this part of chapter 2 at some point, but consider phi for a point charge. Oh, okay, or unless you're able to explain that thing. Phi is about 1 over r. Okay, yeah. Or it scales with 1 over r, yeah. Ooh, how are those $10? Gratifyingly easier. Good. You know, I'm just making this connection. Maybe I have this weird sort of like masochism where like, if I'm not suffering with the physics, I don't feel like I'm learning. And if I'm not suffering in a game like Daisy or Dark Souls or something, I don't feel like I'm having fun. Ugh. I don't know. That'd be easy to see in this case. That's fair enough, Dr. Cook. Yeah, it's just a weird thing. Doritos over 2 and oh, that slashed equals 0. Exactly, it's the famous Dorito squared operator. And it comes in Cool Ranch and nacho cheese flavor. Laplacian. Okay, so we did 75, and it was really in preparation for 76 and 77. Within timelessness, over on YouTube says, "We found on a graphing calculator. I plugged it in but didn't see anything. Can what be found on a graphing calculator?" If you're talking like the thing I had in PDF, like the Laplacian of phi equals 0. That's like a multivariable thing that a calculator probably won't do. Solve Laplace equation approximately for given boundary values using nothing but arithmetic. Based on the relaxation method mentioned in section 3.8, based on the result of exercise 3.75. For simplicity, we take a two-dimensional example. In figure 3.43, there are two square equipotential boundaries, one inside the other. This might be a cross-section through a capacitor made of two sides of square metal tubing. Okay, fair. Integrating over a sphere gives 4 pi r squared times 1 over r equals 4 pi times r. Okay. Divided by the total solid angle of the sphere, 4 pi gives r. I'm glad it's a confusing thing. I don't know. Within timelessness, I'm still not sure what you're saying. 0, infinity, infinity, 0? I'm sorry that I'm not understanding you, but I'm not sure what that means. Like, you want to graph infinity, comma, infinity? That's hopefully not gonna, that doesn't make any, that, like, infinity isn't like a number, I guess. A point within a point? Half, I don't know within timelessness. That just makes no sense to me. I'm not sure what to say about it. Yeah, what's worse, Fenbox, Mathematica or LaTeX in Twitch chat? Integrate sphere slash phi over integrate sphere 1. That's the average of phi over the sphere. Okay. When you integrate phi over a sphere, you get 4 pi r squared 1 over r. But are we getting 1 over r then? Oh wait, but when you integrate, no. Or when you integrate the sphere, you get an r cubed out? Is that what you're saying? In the bottom? Actually, that wouldn't even fix it, that would make it worse. No, I don't know. From an array of discrete points, number that will be a good approximation to the values at those points of the exact two-dimensional potential function phi of x comma y. Make the array rather coarse to keep the labor within bounds. Arbitrary potential 100 to the inner boundary and 0 to the outer. Fucking the fuck out of me? Yeah. As far as I'm concerned, you can curse as much as you want if you're censoring yourself. Or, you know, don't you can censor yourself if you want, but you don't have to do it on my behalf. How points on these boundaries? With the average thing? I don't know. You can see if there's an example with it. It's not an actual example problem. I mean, I can show the proof, or at least the... Oh, the averaging thing? Well, this is just a problem from chapter 3. Like, the one I was working on just in number 75 is on, I guess, page 174. But I think they mention it in section 3.8. Yes, like on page 153, 152 at the when they do that, they talk about the relaxation method and the averaging. Yeah, the theorem itself is like I'm set on 87. I think that my interpretation that I said before was correct, but I didn't say that the charge Q prime was distributed over the sphere. I mean, I don't really care that much about understanding it, like, right now, but... The averaging was simple. Oh, okay. I'm just thinking about it as taking the work you do of moving a point charge, a test charge close to a point charge, and instead spreading it out over a sphere and moving that sphere in just a little bit. I don't know. From what I'm reading the text right now, it doesn't seem like a bad interpretation, but I'm sure that I'm missing a lot of, like, the actual math in that. So with any values at the interior points, but time was saved by judicious guesswork. Judicious guesswork. Why is it so hard to say? Judicious guesswork. That. I don't know if it's a tongue twister or if I'm just dumb, but either way. Between 0 and 100, we expect points within the inner boundary will have higher than those close to the outer boundary. Some reasonable starting values are suggested in the figure. A equals 50. B is 25. E is 50, because you're going over more distance, I guess. F is 25. G is 25. Seems like a reasonable start. That other div, grad, curl, and all that. Oh, yeah. BRB? Okay. The 7 different interior values need to be computed. Go over these 7 interior lattice points in some systematic manner, replacing value at each interior point by the average of its 4 neighbors. Repeat until all charges resulting from the sweep over when no change larger in absolute magnitude than 1 unit occurs across in the course of the sweep. This is still kind of... They make it simpler to make the computation easier. It's still kind of annoying. The first 120 pages, maybe 2/3 through it. Oh, that one, right. Yeah. I think for this one, they want you to do it by hand. And then in 77, they want you to program it, but I kind of just want to program it. Let us agree it'll be time to quit when no change larger in absolute magnitude than 1 unit occurs in the course of the sweep. To your final values. What is that, corrupt? Yeah, so I didn't even read them that closely, but I was like, ooh, this could be something fun. Why is it that just taking the average? Like, I get that it's easy to do numerically, but how is that a solution for the differential equation? Oh, okay, they're explaining it right here. I should actually just read. So the physical phenomenon of diffusion. If you start with much to I value at one point, it will spread to its nearest neighbors and to its next nearest neighbors, and so on until the bump is smoothed out. Hey, Kong Set. I'm probably saying that wrong, but welcome in. It's only going to be a solution if a possible equation is satisfied. Oh, maybe. Killed that poorly. Ooh, shots fired. No, yeah, it's definitely. I've had a hard time with it. Sure, Dr. Cook, if you want to try. So they do kind of boil it down where you only really need to calculate it for one, like, I guess, octant here. A, B, C, D, and why is there? Oh, E, F, and G, yeah. Phrases instead of mathematical variables. He has write out equations. Okay. Okay, that's fair. Yeah, if you don't want to. Sounds good. I can really get that Twitch chat isn't very easy. You can't exactly type LaTeX into Twitch chat. Although, I mean, some people do that, but it gets a little hard to read. Concept. I just want to ask a question, probably not into with your stream. I'm doing an undergrad in biotech, but I want to study math for a master. Do you think I stand a chance? Yeah, I mean, absolutely. Cook, I think I'm happy with my interpretation of 2.1, which is instead of taking one test charge the entire distance, you take it a shorter distance over a bigger surface area. That's my interpretation of it, and I'm happy with that at least. I think it matches what the book is saying. So I'd say it might. I mean I don't know what biotech exactly entails, what type of math that you're studying. I imagine it's a little bit more like engineering-ish and definitely more applied-ish. If you're trying to transition into a master's for math, I would be careful of how the university you're applying to interprets a master's in math and what you want to do. So if you're trying to still stay on the applied side, a lot of universities are going to say that their master's in math, or even for the actual coursework, it's going to be very pure math focused, like analysis, algebra, those types of things. So it depends on what type of math that you want to do as well, but I think if you're managing to do biotech, you definitely have the chops, I guess, to do a math master. You might need to do a little bit of like self-studying if you miss out on a class or something, but I just make sure that you know what you're getting into and look at the actual courses you'd have to take. Both pure maths and applied math. Oh, okay, nice. So yeah, I mean, if you go the pure route, you're probably gonna have a bit more catch up to do. But I think either way, you're when I talk to people who are more like the engineering side of things, they tend to or the classes often gloss over the math details that I learned as part of my applied math major. But yeah, I mean, you're definitely like smart enough to do it if that's your question. Yeah, thanks for the question. I guess I should say the caveat. I only have a bachelor's in applied math. I'm hoping to apply for a master's in math myself this fall. And at one point I was applying for grad school in math, like when I first graduated with my undergrad, but that didn't work out great. Pure math and applied math both damn good. For me, pure math is okay. Applied math is where it's at, though. I think the issue that like Laplacian thing with like rotating it, I think it only applies to infinitesimally small spheres. Like it was based off of this problem, and delta is supposed to be small. It doesn't necessarily like generalize. And hey, Purav Gupta, how much is log 2? Hey, Joseph. Well, there's two different ways to interpret that, Purav, and I'm not sure which one you want. That could mean the log of 2 like this, where there's an implied base. Oh my god, Wolfram, that's what you think I want? What? I can't type this out properly. There. Where they're asking the log of 2, and by not saying a base, they probably mean base 10, in which case it's going to be a decimal. 0.301. But I'm worried that maybe you mean log. Let me zoom in on this so you can see what I mean. Like it could mean this, log base 2 of 10, in which case you plug into a calculator and get this crazy decimal. But if you mean, oh my, please, Wolfram, I'm glad Control Z works. That could also mean log base 2 of some other number that I don't know what that is, in which case this question doesn't make sense and I need more information. You want ln of 2? Oh, well, let's just plug into a calculator then. Hey, 69. Nice. But yeah, just plug into a calculator, you get 0.693147. Because there's no other way to really like do that other than just using a calculator there. That's why log 2 is so easy to remember. Based. That is how I remember 13 squared. It's 169. And that's how I remember 14 squared, which is you just flip those 2 digits to 196. Truncating or rounding up? I don't have a preference, I guess. I never been in a situation where it really matters. I guess always, yeah, I mean, they accomplish a similar thing, I guess. I don't have a preference, though, I guess. I do appreciate truncating and rounding up versus rounding normally, like, you know, sometimes rounding up, sometimes rounding down, because truncating or always rounding up are more predictable. But yeah, I don't have a preference between those two that you say. The Ultimate 32, thanks for the follow. Welcome in. Yeah, it's the gross cherry ones. I have a whole bag of them, but These are one of the things that keep my voice afloat during the stream. So I've gotten used to the taste, but it's definitely that gross cherry medicine taste that it's a little bit less like concentrated, but yeah, I definitely have very distinct memories as a kid of having to take that gross cough syrup when I was sick. It's kind of fascinating that this thing solves the Laplace's equation. I would not think that this would do it. Like, you could use this algorithm to like blur an image as well. Hey, Parav. Or sorry, I already said hi. You can solve JEE Advanced Mathematics question if you like mathematics. I have looked at some of those questions before. They're kind of insanely hard. Lately, I've been working on some like coding projects because that's what I've been finding interesting. So this is a numerical methods project from a physics book that I'd love to figure out. This one's gonna be a little bit of an undertaking, though. Uh, the ultimate. This is I guess yeah. That's what this problem is. For background, I've been doing a reading group on electricity and magnetism out of this textbook here. We have like actual reading groups on Saturdays, and this is just something I do in the downtime of my math streams while I wait for someone to ask a question. Thanks for that $10. And Dr. Cook, I guess if you're in my Discord, you can put it in there, or if you want to, if there's a Discord you're in already, like Zach's or Penn Center's, I'm sure they wouldn't mind if you put it there. Just wherever you do put it, let me know. So yeah, I've been doing a reading group on this book on officially on Saturdays, but if there's downtime during a math stream like there is now, I'll sometimes get some problems from it. And I was interested in doing this problem at the end of chapter 3 that is getting a numerical solution for Laplace's equation. So that sounds like computational electrodynamics, I guess. Oh, Dropbox works too. I'm probably going to fail miserably at it because I'm terrible at coding, but I'm trying to remember how to code. So, put in your Clifford algebra folder. Okay. Just making sure before I show this that I'm not going to accidentally like show something I don't want. I think we're all good though. Here, maybe shy. I was trying to write fast. No worries. Uniformly distributed. Okay, so key prime is uniformly distributed. Yeah, let me bring up theorem 2.1 again. If phi of x by z satisfies the Laplace equation, the average value of phi over the surface of any sphere is equal to the value of phi at this. Oh, wait. So the sphere doesn't need to be centered on the charge? Like, this is the charge that we're measuring phi against, but the sphere is way over here, not even intersecting it. Or containing it. Like Gauss's theorem. The typo after typo. So Q prime is correct here. E sub Q prime due to Q prime is KQ prime over R squared R hat outside of that. Okay, I agree with that, yeah. I assume that's phi. KQ Q prime over R. Or U, amount of work required. Oh god. To construct the above configuration, bringing Q in from infinity. This amount of work we've done to construct the above configuration, bringing Q in from infinity. Okay, yeah. Oh, W. Okay. Oh. Okay, that makes sense. The same work, W, if you fix Q and instead bring in Q prime. But this requires W equals Q prime Is that a cross product? I don't know what's happening here. So this the angle brackets make me think of a vector, but I feel like I'm misinterpreting that. I mean, that's just, well, Q prime is a scalar. I can't read this part though. Or maybe Q prime. I don't know like what values in this part here. Similarly, like down here, I don't know what this part is. The work required to bring the sphere in? Is that what that is? The work required to bring in Q prime? Phi sub Q sub S is the average over S. Okay. Q prime. Okay, yeah, so just if we have phi sub Q, we can multiply Q prime to get the work required. Okay. Oh, shoot, I'm sorry. I'm getting a call and I need to see who that is. I'm gonna be back in a minute. Okay. Sorry about that. It was just silence on the phone. I have no idea why that would happen, but it took me a few minutes to actually get my. I used my phone as my camera there, and so it took me a few minutes to actually get my phone like set up again. I'll do some more. This is not so easy to express. If you want to talk, we can. If like, or do you want to use Discord to do it, or do you just want to? I don't know. If it's too like annoying logistically, we can just forget about it. I see someone joined the Discord. If that's you and you want to talk, just join the waiting room chat, I guess. Get a bit more. Okay, okay. Oh, and also, hey, Bob. I hope you're doing well. Oh, shoot, you're right. It's not. It isn't on stream, is it? I don't know. Like, it was just a call I got, and like, no one no one talked, and I gave them a minute to see if they would call back, and they didn't. So, I don't know. Someone's robot probably glitched out. That seems like a weird problem, Purah. Is it solving that for X? Oh, was that okay? You just joined. Um. Hey,
Hey, what's up?
nothing much. How about you?
Doing pretty good. Are you ready to talk this out? Um,
Yeah, I think so.
okay. I did you refresh? I added a few. Oh yeah, you
Yeah.
got the new version. Yeah. Okay. So the key idea is to consider the amount of work to construct this configuration as shown at the very top. You have a point charge on the right, Q, and you have this Q prime smeared uniformly over a sphere S on the left. If you bring both of those in from infinity in some way, it requires a certain amount of work, and that work is going to be the same no matter which order you do it in. Um, so the
Okay.
first way we do it, consider bringing the Q prime in first on that sphere S. And then everywhere outside that sphere S, because it's uniform, the electric field acts like a point charge. So the electric field due to Q prime, even though it's over an S, if you're looking at that electric field outside the sphere, it's like a point charge, KQ prime over R squared. But the key idea is that outside of S, the charge Q prime acts like a point charge centered at S. That's Gauss's theorem.
Great.
Okay, so if we bring in Q now, you, since that Q is coming in from infinity to R away, it's always outside the sphere. We can calculate the energy it takes to bring Q in from infinity, treating Q prime as a point charge. That amount of work is just KQ Q prime over R, big R. We're allowed to treat Q prime as centered as a point charge centered at the center of S during that whole process because of Gauss's theorem.
Right.
Okay.
Is that the
So
entire
now we're going
thing?
to
Or okay.
now
Go
we're going to
on.
compute that work in a different order. So if you scroll down to maybe the green text, so now we're going to compute in the different order.
Oh,
We
that.
bring in
Okay.
we bring in the Q prime in first. So now the Q prime is sitting there smeared uniformly over S. Oh, I'm sorry, did I just say this wrong? Yeah, sorry. I bring in the point charge on the right. I bring that in first. So the point charge Q is sitting there on the right. And now I'm going to bring in Q prime over the sphere S. Now, however much work that costs is going to be the total charge Q prime times the average of the potential created by Q over the sphere S.
Why is I guess like why is the average of the potential being involved in the first place? If it's uniformly distributed over the sphere, it seems like the average doesn't seem like a significant thing.
So like on the right side of the sphere is closer to Q. So the potential created by Q is larger there. 5Q is larger on the right side of S than the left side. It was closer to
Okay.
Q.
Okay,
So
fair.
to do, yeah, so the total amount of work is just going to be the total charge Q prime over the sphere times the average value of the potential on S. And I use this kind of heavy notation, but I'm trying to be maximally clear. So the angled brackets mean average, and the subscript S means average over the sphere S. And 5Q means the potential created by Q. So the point charge Q creates this potential everywhere in space. I average that over S. I get some average potential on the surface of S. And then I multiply it by the amount of charge I'm putting on that surface S. So that charge times that average potential will be the total amount of work.
Huh. Okay.
I mean, it's kind of okay, think of phi as like money. It takes more money to bring in charge close to Q because phi Q is larger there. So to bring the Q prime on the right side of S takes more work than it does to bring on the left side of S because the left side of S is farther away from Q. So if I just want to multiply by Q prime and get amount of work, I need to use the average value of phi over S. It's greater on the right side, smaller on the left side, but the average value times the total charge will give me a total amount of work. So does that part make sense? That's kind of the key idea.
Well, the average almost seems like too clean of an answer. Why isn't it some crazy integral adding up like the path of just like the right bit of the sphere as it gets closer versus adding it with like the left part of the sphere as it gets closer to every other part?
So the integral is hidden inside of this average.
Okay. I guess I can just accept that it does come out to be the average. Like that's the part that's weird. Like, why is it just, the average just seems like almost too clean.
Let's see. I mean, I think you're maybe worried that the Q prime will get stuck inside the integral, or like the dQ prime. Every little bit of Q will get stuck inside the integral or something.
Yeah, it's just like, it's great if this is true, I guess, but it almost seems too good to be true. Like, yeah, there's some thing that does get stuck inside the integral.
Well, I can try to write that out a little bit more, but let's suppose that for now.
Yeah.
Let's suppose that for now. Now, if you equate those two expressions for the work that we did in both orders, the Q prime drops out. So we get the average of phi over the surface of the sphere S is KQ over R. The KQ of R is also the value of the potential created by Q at the center of S, because the center of S is a big distance, a big R away from the point charge Q.
Okay. Yeah, KQ of R just happens to be phi 2 to Q, and that's how we get that equality with the average of phi.
Right. So
Okay.
so at the very bottom, if you equate that again, you get the average of the potential created by Q averaged over S is equal to the exact value of Q at the center of S.
That's weird, but that does help me understand what's actually happening. So I was definitely picturing the complete wrong thing in my head.
Let me. So my iPad is connected to Dropbox right now, so I can try to write integral that you're talking about, because actually now you've got me a little worried too. I mean, it's going to work out, but I see your point. I see your point. So if I edit this and then re-upload it, I think you can just refresh. This might take me a minute or two, but
Okay.
maybe I can hop off in the meantime.
Uh, yeah, sure. I guess then if you work it out, you can hop back on.
Okay. Okay. Hopefully I write it clearly enough. Sorry that was so sloppy before.
No worries. I appreciate that you're like even giving an explanation in the first place, or that you're trying. So, thank you.
Well, it bothered the heck out of me because I saw it first and I was like, "What the heck is he saying?" And then I had to read it like 3 times, and I was like, "Oh, okay."
Yeah, I thought that that Q and Q prime have the same center, so I was going about this completely wrong.
It was confusing. Yeah, I thought like it would be centered on one of the charges, the sphere S, but it's not. You have one charge outside the sphere, and there are other charges on the surface of the sphere. So that's the origin of his first comment at the beginning of the proof. He says, we're not going to consider the general case where there's charge inside our sphere S. We're going to assume it's outside. That's why Q is far away on the right.
Oh, okay. I misinterpreted that sentence too. I thought that was like some trivial case where there is no like Q charge to do work against.
Yeah, he's very. Yeah, I sympathize with you guys now. I haven't read this in a while. This is confusingly written. I would agree with that.
Huh.
Okay.
Okay.
Let me. I'm gonna hop off and try to write this out because I don't want to hold you guys up too long. I want to get this explained quick.
All
That's
right.
bugging me too now.
Well, thank you.
All right.
Talk to you in a bit, hopefully.
Okay. In a bit. See you soon.
Okay. Hey, Klassen, how's it going? So yeah, for anyone who's not aware, that was a Dr. Cook right there. He's been streaming retro games like Mario and physics and Clifford algebra. So should probably like that. Yeah, like yeah. I mean, Dr. Cook it is awesome. It's pretty like it it should be true because of where we're using the fact in this theorem, but it's definitely it seems like interesting to me that if you were to integrate like maybe it'll be easier on this one. If you were to do whatever integrals involved in taking this little piece of the sphere, bring it from infinity to this fixed distance, plus this piece of the sphere, bringing it from infinity to that distance, plus this piece of the sphere from infinity to that distance, that just happens to come out to the average is kind of wild. Klassen over on the YouTube chat. I think it's very brave to assault this text without a teacher, like climbing Mount Olympus without Sherpas. It's a nice metaphor because yeah, this one I probably should have looked up some kind of outside resource for it, but it's just there's so much like content to get through that I feel like I can't spend that long on one piece. Oh, I mean, never been a guest. Well, you did a great job, and I appreciate you like coming on. Yeah, I'm sure it feels weird. Like, it felt more weird to me at first, and then I got used to it. Klassen is saying, we're gonna send a pic. Yeah, if you have a picture, you can put it in my Discord. Your question is two thin circular disks of mass m and form having radius of a and 2a respectively are rigidly fixed by. Oh, this feels like a physics problem. Let's see if we can figure it out though. Put it over in the Twitch chat too, at least however much is there. You have some kind of a lopsided, like, two wheels that are different sizes connected with an axle, it seems. I don't think that I can do this. I remember so little about angular momentum. I can picture this thing basically spinning in circles with the smaller one as the center. Or maybe not as, that might not necessarily be true, but spinning around in circles with the bigger one on the outside. But yeah, this is pretty firmly in like physics and mechanics, and I really don't remember how this works. Um, it's kind of interesting then that like this is related to Earnshaw's theorem. Where do they use it? In the second proof. Average value of a sphere is always equal to the value at its center. Clearly, neither is possible. Hmm. Either lower than that at all neighboring points or higher than all that at all neighboring points. I have to think about that more, I guess. But in the meantime, I don't even know how to describe this. It's a Laplace's equation in a two-dimensional potential surface inside of another square equipotential surface. Okay. So maybe let's solve 3.76 first. And that'll inform how we can do 3.77, which is just an extension of 3.76 for a more arbitrary, for like a finer grid. Oh, well, thank you, Klassen. Yeah, I think that the idea of like a math help stream like this, it's kind of wild to me that it's not more popular, or maybe I'm just not aware, or if it is popular, I'm not aware of where that's happening. Over on Twitch, there's like this little niche of a couple of people, but even then, it's not too big. And on YouTube, I'm not really aware of anyone who does it regularly. Uh, I feel like we should just manually define the array as the book gives. Well, just this little, I guess, octant. Okay, so yeah, Klassen, thanks for posting the entire question, but like I said, I don't think I can do this. My physics is really rusty. I can Google it and try to explain it if I can find the answer, but like, or maybe someone in chat has an idea and wants to volunteer to help, but I definitely cannot. I don't know how to do this off the top of my head. Hey, Antonio. Oh, is that Portuguese? I don't speak Portuguese. I only speak English. So yeah, class, the best I can do for you here is Google it. But I do math. I sometimes attempt and fail at doing physics, but this is physics and not math. This is like the same problem. Oh God. Yeah, so this is going to be too long for me to really be able to reasonably understand anytime soon. I can link you to this. I can't explain that one to you though. Or I'll put it in the Discord too, but I don't know how to do it. Oh, you posted it twice? I'll put it there too, just so if anyone looks at it, they'll see at least there's that much. But like, yeah, I don't know. I can't do that. Oh, good. Okay. Okay. So I think I'm just going to manually create this array here. We're going to have to figure out a way to make it more generally for the next part, but it's a problem for future me, I think. Okay, so I've been getting, I don't know why, but I've been getting really confused about multidimensional arrays and if I'm writing the rows or the columns first. These, I think it just looks like a normal like matrix when I write it like this. So I'm going to go 0. Oh God, I need to see the initial guesses. B prime, or the initial guess for B, what? Where? Oh, it's cut off. 25. Then the initial guess for A, it's 50. And then we get to the equipotential surface, which is 100. And then we do comma, and then I think we come down here and we'd have another. Oh, we need. No, we're good. Now we go 0, BA 100, which is the same as above. Uh, 0 DC, D is 25, C is 50. Would you look at that? Same exact thing again. Now it's 0 FEC prime, 0 25 50. I'm not gonna remember the fourth one. 0 25 50. And then C prime, which is C, which is 50. And then 0 G F prime, 0 25 25, 25 25. And this one, we're never going to use this value, among a few others, but we can say it's the same type of point as D, and D is 25. So I think that's the array that we need to do, and we're worried about oh, I'm counting from 0. Ah, man, it's fine. I'm just gonna leave that as is. Actually, maybe it's more clear. A, B, C, D, E. We don't do the parentheses when we define it. Actually, is that? I don't know. 50, 25, 50. $50, 25, 50, 25, 50, 25. These are the initial guesses, and then I really should have filled in B0 equals 0, B1 equals 100. I really should have done it like this, I think. Make it a bit more clear. What's actually happening with this matrix. That's A. That's B. That's B. No, I got them reversed. That's B. Nope, that's B. That's A. That's B. That's A. That's D. That's C. F. E. G. F. D. C. Oh, sorry, I forgot to zoom in. You're right. Oh, that's not the right type of zooming. Scroll and drag down. That's not doing anything, but I do need to zoom the text. Zoom it doesn't save that. To edit multiple lines. Oh! Really? Oh my god. Wow, okay. I never knew that was a thing. Thank you for that. Oh, wait, Control Plus. Oh, that's zooms everything in though, which I don't like. I guess we can back those out. Just make the. I feel like the code isn't quite legible in stream, so I just want to make sure that it's that it is legible. Oh wait. Oh, they didn't list it. We need values below that G there, so we do need one more line in this array. B0. This is just a boundary, so they're all phi 0. Like that. So these first two B's and A's are, the book gives them as B prime and A prime. And these are gonna just always be equal to B and A. The fact that, like, we need to, we don't take the average of those B's and A's, we just use them to calculate the ones below. Same with this C here and this F there. We're really just interested in BA, this DC, this FE, and this G. And so for each of those, we're going to do a pass where we take the sum of, like, if we take this D, we're going to take the average of the thing above it to the right, below it, and to the left, and that's the new value for D. So all these phi zeros on the border are going to stay the same. All these phi ones stay the same. This B and A, I guess, get set to whatever this B and A were after they just get changed. And the FE, DC are similarly going to stay the same. Or they're going to track whatever FE and C are elsewhere. which I'm gonna have to do that manually, which is a little bit annoying. Unless there's a way to make it track automatically. But we are going to stop this averaging process once the change becomes, the maximum change becomes less than 1. Max change equals 1. We just need to set it to anything more than 1. While change is greater than max change, we're going to take phi of, I might transform it into a for loop, or I don't know if it'll be easily. A for loop isn't like the best thing, because we need to keep some things constant, some things not. So phi of row 1, column 1. Oh, you're ready for round 2? All right. I'll drag you in just a second here. Hey.
Hey.
Okay. So I just
am
refreshed.
I audible?
Yeah, I can hear you.
Okay. Okay. Cool. Cool. Is it all looking okay? Like you can see everything?
Yeah, wow, looks like you were busy.
Well, I think there's a quicker way to explain this, but I realized from our previous discussion it might be better if I just try to be like maximally explicit.
Okay.
Okay. So yeah, so as the part I underlined, that's the new stuff. We're trying to explain this average, why this average of the potential created by Q averaged over S, why that term is coming up, or maybe how it's coming up. So recall that in this part, we're imagining the point charge Q on the right is fixed, and we're bringing in Q prime on the sphere S. So to do this, we can break up that charge Q prime on the surface of the sphere S into little chunks dQ prime, and we can just calculate the work for each between the work required to bring each dQ prime in, and just integrate that. That's I think this is kind of the origin of your objection earlier, that each of these little dQs will change. Like some are like, so this R prime will change as I bring in different dQ primes.
Yeah, it's just like really weird to me that that would be true.
Yeah, so let's see how that works out. So I drew one representative dQ prime on a point on the sphere S. And maybe we can come back to it as needed because there's a lot going on in that picture. So the charge is distributed uniformly over the sphere S. Oh, and notice in the picture I gave it radius A. So the charge density on the sphere S is the total charge Q prime divided by its surface area 4 pi A squared. That's sigma. Sigma is like the Greek S for surface charge density.
Oh, okay, yeah.
Okay, so it has units of coulombs per meter squared. Okay,
Right.
so we're gonna build up this total Q prime by bringing these little dQ primes in. And here I wanted to get a useful expression for dq prime. It's the charge density, sigma, times the little infinitesimal area, dA, on the surface of the sphere that the dq is located at. It's like the little green patch in the picture.
Okay.
Okay. Now that little dA, as I show in this calculation here, has value a squared, the radius squared, times the infinitesimal solid angle d omega. And if d omega is confusing, it's like you take the total area of a sphere and you divide it by the radius squared you use. That's always 4 pi for every. The same way for the total angle on a circle is 2 pi, because the circumference is 2 pi r divided by r, you get 2 pi for every. It's like the size. And I also wrote it below in white if you want it like it's that factor you always have to put in the angular integrals if you like spherical integrals.
Okay, yeah.
If you integrate that over the full sphere, you'll get 2 pi, or sorry, 4 pi. So you should think of like,
yeah,
a circle has total angle 2 pi, a sphere has total solid angle 4 pi, and you can generalize this to higher dimensions, but this is useful for spherical stuff. And it's the same way for like if I take a little arc of a circle of radius r, the length ds is r d theta. The same thing happens with a sphere. The little infinitesimal area of a patch dA is the radius squared, because now we're talking about area, so a squared times the infinitesimal solid angle. So this green equation by the picture, that's analogous to like ds is r d theta for the arc of a circle. It's like just one dimension higher.
Okay, that makes sense.
And even if you don't like that, what we end up getting is dq prime is q prime times d omega over 4 pi. And that has a very like natural interpretation. To get the amount of dq prime on that chunk, I take the total charge q prime and I multiply it by how much fraction of the sphere that solid angle is taking up. And I can do that because it's a uniform charge density. If the charge were not uniformly distributed, this equation would not be true.
Okay, yeah.
Okay, so now that we have this little dq, we can calculate the amount of work dw. We're bringing an infinitesimal charge, so it's going to require an infinitesimal amount of work. So dw is dq prime times the potential created by q at the point r prime, and that's defined in the picture in purple, if you see that. So is that? I think this is kind of getting at the heart of your objection. So I want to make sure you agree with that.
Right, so the difference in work is equal to the difference in q prime times the potential.
No, not difference.
Or sorry,
you should think
differential?
Infinitesimals.
Or infinitesimal, yeah.
Yeah. Just think of like a very small amount of work.
Right.
Near zero. Yeah.
And syntax, I don't remember what integral I mean, but sure. In hey, Hergy.
All right.
Sorry.
I didn't quite.
Sorry, I there's a couple of us in chat that I wanted to address, but I think is really just taking the phi generated by q, multiplying in the infinitesimal part of q prime, and then we have this r prime vector that's part of just work.
It's the potential created by q evaluated at the point r prime, so it's like inside the.
Okay.
So the big picture idea here is, as you correctly said,
that's of a function. Yeah. Okay.
Yes,
phi of r prime. Okay.
Yes. So as you said correctly earlier, this dq, if I consider the q prime as like a macroscopic hole over the sphere, every little piece of it is different distances away from q. So the way to overcome that is to break this q prime into chunks, and each little chunk is one distance away from q. So we have dq prime is this fixed distance r prime away from q. So now I can just do a multiplication. The cost is that I have an infinitesimal thing, but now the work is just a multiplication because there's only one distance in here, r prime.
Okay, I think I'm on board with this then.
Okay, so now I just poop in dq prime from above. It's the total q prime times the fraction that the solid angle where the chunk is sitting.
Right.
So now that's the infinitesimal amount of work, and we're very close. That's the infinitesimal amount work to bring this dq prime in. So now I just need to add up the work to bring every dq prime in. And that will give me the total macroscopic work. So I have to integrate the dw over the sphere S. And it's a double integral because it's a two-dimensional surface, the sphere.
Right.
So then the next line, I just put that in. And I pull out the q prime, that's a constant. And I pull out the 4 pi, but I put it down below for a reason. Because I replaced 4 pi with the integral of d omega, the solid angle, times 1. So, yeah. So
Wow.
the 4 pi is like the 4 pi is the normalization. Like if you wanted to average a function over a circle, you would integrate over the circle, but you divide by 2 pi to account for the total angle of the circle. So when we're averaging over a sphere, you need to divide by 4 pi, the total solid angle of the sphere. And that's why that 4 pi was there.
That's crazy how that works out. Thank you for showing it.
Well, you gave me a pause there. Like I have a PhD, so I really should know this. So it was good to verify to myself that I do. Are there any questions about this? I really like your high level. Yeah, how to say this properly? You don't let you're not letting me smooth over gloss over details, so that's really good. So I'm attack away. I'm ready.
Okay. I appreciate it. What?
Is any part of this like objectionable, or you want to talk a bit more about?
I'm thinking about it. I think the end part I'm completely on board with, like purple and below. No objections there. As well as the blue part. I guess it's still, I'm still a little bit thinking like the d omega over 4 pi part in the very first part for dA. Oh, I guess you're taking the total surface area and multiplying it. Okay, no, I guess I get that now. You're taking the total surface area and getting a fraction of it.
Oh yeah,
based on
yes.
d omega.
Sorry, I should have explained that there. Yeah, but you can also just see it straight from the result, a squared d omega. Like I said, that's analogous to an infinitesimal arc of a circle would be a d theta. I'm sure you've seen that. Like,
yeah, they use that all
so
the
this
time
is like the two. Right. So this is how you do that on a sphere. To get the surface area of a little infinitesimal chunk, you take the radius squared and you multiply by the infinitesimal solid angle. And just like in the one-dimensional case, the equation S equals R, or ds equals r d theta, that only works if you measure the angle in radians. In fact, that's how you make that equation true by defining radians. And the similar thing happens here. So this defines a unit for a solid angle called stir radians.
Okay. Yeah, I've heard the term stir radians before. I don't know much about them though. But that makes sense.
It's just like you define radians to make a straightforward relationship between the radius and arc length. Like angles doesn't. If you measure an angle in degrees, you can't use an equation like S equals R theta because, like the 360 degrees in a circle is just chosen to be that way because it's highly divisible number. I think that's ancient people did it that way.
Oh.
But you defined angles to you define radians to be you take the arc length S at subtens and divide by the radius. So by definition of radian, the equation S equals R theta is true. Like that's yeah. And the similar things happening here with stir radians in the solid angle. Yeah, and Finvox is bringing up an interesting point in the chat. Yeah, we're considering just the work between the two charges, not the self energy of the sphere S. That's a good point.
Yeah, and I think that's like intentional. Like that's what we're supposed to do. We don't care about the energy to assemble the sphere. Oh, and see it, Hargi.
Yeah,
sorry.
The energy is there. It costs energy to assemble that, but it's not relevant for this argument. We're just because if we look back at what we calculated before, in the first way we calculated work at the top of this document, we also didn't include the self energy of S. We just assumed it was there, and we calculate how much work did it require to bring Q in. So yeah, so that answers Finbox's question more directly, I think. We didn't take into account the self energy the first way when we assumed S was just given. We just calculated, we assumed S was given. How much additional work does it take to bring Q in? So we shouldn't count that self energy when we calculate the second way.
Okay. I think I gotta let it like sink in, but like this is really like really helpful. So thank you for that.
Well, man, like I said, I jumped to this part in Purcell and I read it and I was like, what the hell is it saying? And that made me have so much more sympathy for you guys. Yeah, dude, this is a tough book because I kind of knew how this all was going to work out ahead of time. So that's kind of the only reason I was able to do this. And so, yeah, approaching this for the first time, those would be like hieroglyphics. What Morin is saying. Yes, I feel your pain,
Feel
Finbox.
Okay. I think some people in chat were gonna ask like some type of like math questions, but sorry, what were you about to say?
I wanted to see if there was any other issues, but if you want to go to other stuff, I totally get it.
Oh, I don't think there's anything for me. I assume Finbox already asked his question, so.
All right.
I think I'm all good, yeah.
Awesome. Okay. I'm glad this worked out. That would have been really bad if I couldn't have done it. So thanks for letting me come on stream.
No, thank you.
Sure. All right. I'll be back in chat. See you in a bit.
Sounds good. See you. Okay. So yeah, sorry, I got a little bit behind on chat there. Oh, you're the person who posted that integral syntax error. I don't know anything about it, but like that second change thread was like the best that I could do there. But if you want to talk about it, I can try. But yeah, high and by Hargy and central high, and of course I don't acknowledge you because you're just not important to me. Why don't I have a PhD? Because I don't need a piece of paper to prove how much of a genius I am. I don't know. I want one. Claston says integration sucks. Integration is fun, I think. Oh god, Neon, you want the derivative of tangent to the tangent to the tangent? Oh, yeah, shoot, I shouldn't have closed that tab. Let me download it quick. Okay, I have it downloaded, so you do whatever you want with that. He's gonna go cry now. You're welcome, Central. How do you take the derivative of tangent? You have to do... I don't know how you do that. If you had... I don't know how you do it with two levels of exponents. I guess let's explore it. I can erase everything that's on the whiteboard. I don't need this anymore. Oh shoot, I'm not charging my phone. Now I am. By eraser? Yeah, so I assume if it is possible, you have to use that same trick with exponentiation and just be crafty. So the question is, what's the derivative of tangent x to the tangent x to the tangent x? Oh, cool. Thanks for the Wikipedia link there too. So let's try at least doing it with one level with, well, yeah, I guess. E to the tangent x to the tangent x times ln tangent x, right? This would simplify the way that we want. Now if we do the same thing here, how will that look? Just bringing the part that we know first. So that's that. And now on these two, we do e to the tan x ln tan x. That's a problem. Well, yeah, that's a problem. If this was plus, I think we'd get something we can work with, but it's not. Is there a chain rule? So actually, maybe we start deriving this. We know from taking the derivative of the outside, we get the same thing back. But now we need to multiply, oops, and when I'm switching to partial derivatives, d by dx of just the exponent now. And I think maybe now we're in business. Because we can product rule this thing and we know how to take the derivative of each of those parts. Hashtag differentiate, not the chain the rest of your life. Oh wait, let's catch up with chat. It's for the value of x equals pi over 4. Can't you use product rule and x to the x differentiation? It'll be something like that, yeah, neon. This bit right here is just the original expression back. Having the second level of exponent, like having that tangent x up there, it's going to make it a really similar format, but a little bit more complicated than just x to the x. So now we do product rule here. 1 over tangent x. Tangent derives to secant x tangent. Oh, really? So we get just secant x. No, tangent derives to secant squared. Ah! Secant squared x over tangent x. Secant derives to secant x tangent x. Okay, so that's the derivative of ln tangent x. We multiply by the original of that. And the original of that is just, I'm going to tan x to the tan x. Plus, now we keep that constant and we take the derivative of this. Which is just the same thing back. Tangent x to the tangent x. Chain rule times the derivative of the inside. Ugh. Which is secant squared x ln tan x plus I think secant squared over tan x. Okay, that's actually not as terrible as I thought it'd be. And they're saying to evaluate at x equals pi over 4, which I guess we're ready to do that. Blood is starting to come out of your ears. Figure out simpler. Oh, yeah, probably do that too, Phobos. I feel like this wasn't that hard for me to follow, though, the way that this is. Evaluated at x equals pi over 4. Tangent of pi over 4 is 1. So we get 1 to the 1 to the 1 times secant of pi over 4. Secant is 1 over cosine. Cosine of pi over 4 is root 2 over 2. So secant is just root 2. But we square it to get 2 over 1 times 1 to the 1. Plus ln of 1 is 0. Oh, hey, and who even cares about any of this other stuff? Because it's all times 0. So we get 1 times something, which is just something. The something is 2 times 1 plus 0. We just get 2. It's funny. It's a complicated version of 2. Saying yep, so I assume you're on board with that. You got 2 as well, Dr. Cook? Awesome. I said you had a second question as well, Neon? It's kind of a fun little derivative there. I'm gonna deal with... I don't care about colors anymore. I want the bigger and better things. Classing gets 2 as well. Awesome. You want to know about magnetism, the relation between that and current. Oh, I'm not a very good person to explain that. I am studying electricity magnetism, but if you're asking me the relation between current and magnetism, I hardly remember. I know that I remember that current generates a magnetic field, and I believe that magnetic field runs in a circle around that current. That's about the total of my memory of how magnetism works. So I do happen to have an E&M book right in front of me, though. Oh, I mean, that looks relevant. The magnetic field of that time and place is defined as a vector B that satisfies the following vector equation. F is equal to the force from the field plus the amount of charge moving with a certain velocity crossed with B. Oh, hey, Isaac Newton. Biot's Savart law? Oh, let's look at that. Should my teacher in our school? Oh, thank you, class. That's a cool looking figure. You're gonna make constant electric current. I'll drop a link in the YouTube chat too. Hey, the 7 War, if I'm saying that right? B.O. Savar. Oh, you don't say the T. You don't say the T in either of these? I feel scammed. I want to say the T. Drop the T then. How to do the right hand thumb rule and Flaming's left hand rule. Am I familiar with mechanics? Not really. I'm terrible at mechanics. Yeah. No, I think it's funny that there's two names rolling T and you don't say it in either of them. An A tier joke. So you heard how to do the right hand thumb rule? I guess for the magnetic field? That's a good question. This seems relevant. Or is it? What? Oh, that's at a given... Okay. You can do the right hand thumb rule with the left hand if you stand in front of a mirror. This is a fun fact. Yeah, to some more, feel free to try to explain it because I am trying to study E&M, but I'm not anywhere close to magnetism yet. What is Flaming's left hand rule? Oh, Fleming's. Oh, it's just the same thing, but you call it the left hand rule. Okay. DELL is an indivisible chunk of wire carrying the current. Direction given by the local direction of the current. Intensifying magnetic field dB. This, I'm a little stuck on this picture. This picture feels a little arbitrary. I feel like I can, like, why can't I do, you have to hold your thumb perpendicular, I guess. I guess you have to, like, freeze your hand. Well, I guess you can move your two fingers like this to match the angle between IDL and R hat prime. And you would integrate over all of those dBs. BYJ using for familiar with their course ads. Oh, the site comes up a lot whenever I Google things. I looked at it a lot. I know hardly anything about it though. IDL cross R prime. 9 plus 10, 21. An emoji for right hand rule? Yeah. Huh. The thing is, like, I always saw the right hand rule in like a different. That's not the way I was taught to look at the right hand rule. I would you start your hand like this, you point it in the direction of one of the vectors, and you curl your fingers in the direction of the second vector. So like this thing, I'm trying to work out how you actually use it. I guess that's probably an equivalent thing. Is it? Yeah? No? Maybe? I mean, I don't know. It's a meme class in 9 plus 10 is 21. Diagrams are cracking you up. With the hands? I'm trying to like work out how to use them. It's equivalent to my way for the finger curling too. Wait. Oh, this is for a motor. That's why the labeled things are different. Oh God, Isaac Newton. Are you asking what implicit differentiation is, or are you asking how to take the derivative of x to the x? Because that's two annoying problems wrapped into one. What you just put in chat there. So yeah, I don't have a good explanation for you here, Neon. I'm getting a little bit stuck on where to put my fingers, which I didn't think I'd be saying in this context, but here we are. I need a Wikipedia article to show me where to put my fingers. That's what I'm trying to say. Well, Isaac, which piece are you confused on? Do you if you had the derivative of x to the x, do you know how to do that? X to the tan x? I feel like okay, so you do know how to take the derivative of x to the x. Okay, so I'm gonna gloss over that part a little bit then. I would think that taking the derivative of x to the tan x is harder than x to the x. Unless you're saying there's going to be some kind of like nifty cancellation. So if your problem is find dy by dx of, so y to the x plus x to the x plus x to the y equals 0. So the real problem here is implicit differentiation. Thank you. Yeah, but $10. I remember like half the time. Yeah, you differentiate it separately. You do d by dx. Of each of these. And so using the trick, I'll do it on that one. ln y. You get y to the x times why isn't my brain working right now? Product rule on this. ln y plus x over y. And then we took the derivative of something involving y, so we multiplied by dy by dx because of chain rule. So that would be what you get for the first term there. And then we were saying x dx, was it 1 plus ln x? I should be able to just tell from that, right? Yeah. And then the derivative of that, I'm just going to take this and switch the x's with the y's. I'm sure it'll work, right? We still multiply by dy over dx, though. And now, you can subtract this piece to the other side, factor out the dy by dx, and divide everything else over, and you solved for dy by dx. Not the whole bracket? Oh, well, are you sure, Neon? You're saying the dy by dx only goes on this piece here? I think it goes on the entire thing. Or does it? You might be right. That's a little, that's annoying. Okay, there's a little piece that I'm not sure of here. Neon is saying that it should look like that instead of the dy by dx is only on this piece. And now I'm not so sure who's right between us. I'm gonna put it back to how I wrote it originally, but I might be wrong here. Maybe Wolfram Alpha will save us. But yeah, I was wondering, like, we took that very first one, the y to the x, involves taking a derivative as well, which is why I put it on the outside. That's why I'm getting a little confused on. Y to the x plus x to the x. Wolfram Alpha is going to hate me. Oh, it's doing a partial. Wolfram, you're kind of the worst sometimes. Furthermore, oh, thank you. Okay, Wolfram did. Not even Wolfram wants to do this. No, Wolfram is just going to do it with a partial derivative. I mean, if I give it this, what does it do? I don't know how the implicit differentiation... Oh, yeah, Phobos. Forcing Wolfram to recognize this as a function of x. Hey, that's... Oh, and Neon's right. Okay. Great call, Phobos. Well-deserved save that I always forget to give out. Thank you. It's 5:10 in the evening for me on July 30th, Isaac Newton. So yeah, I guess we didn't actually take a derivative of y until we got to that piece. But I thought that this kind of involved taking a derivative of y, which is why I put dy by dx on the outside. Apparently not, though, according to our Lord and Savior Wolfram Alpha. So I'd say that's more accurate. Oh, yeah. You're right. Good call there, Neon. Headers now? Alright, see ya, Klassen. Vinay asked about the integral from 0 on the left to pi over 4. Or no, I think that's a typo, the 0. Of x over sine to the 4th of 2x plus cosine to the 4th 2x? Yeah, I'm in California. Oh, that looks terrible, Vinay. I'm gonna be sneaky and put this into Wolfram Alpha because I want to see if it's something that's like absolutely disgusting before I look at it too hard. X over sine 2x to the 4th plus cosine 2x to the 4th. Kind of inviting you to use a half angle, but I don't like the look of it. Yeah, Bay Area. Ooh, does it? Ooh. No, it's not numeric. It doesn't want to tell me how to do it. That's my street address? Oh, good. Okay, so Wolfram Alpha, it gets an exact value. It doesn't want to tell you how, though. It's unlucky. What's the integral? It's all crash at my place. Yeah. Could have DonCon. Variable further bound. Ooh. You lived in the Bay Area for a long time. It's a nice place. What the? Really? Okay, well, let me try Phobos' idea first. That's still kind of, I don't know how we would integrate that. Is that a virus stress sub? Even then, I think the X on top might mess that up. And actually, that's kind of a disgusting result there. But it is a definite integral. Oh, Wolfram Alpha doesn't like that. X over cosine 2x to the 4th plus sine 2x to the 4th. How does Wolfram Alpha simplify this? Does it get the same thing? Oh, that's a cool graph. Okay, so it is apparently possible to simplify it to 4x over cosine 8x plus 3. Father Wolfram is not pleased. You don't say if you don't want, but where are you around now, Dr. Cook? Okay, 4x cosine 8x plus 3. 4x over cosine 8x plus 3 dx. Is that right? What? This one, 4x cosine 8x plus 3. Okay. Oklahoma. Oh, cool. Oh, Wolfram Alpha still doesn't want to tell me how? The winds come sweeping down the plains. I mean, I haven't been, so maybe I shouldn't judge it. I feel like I probably wouldn't enjoy living in Oklahoma. But maybe I'm just being a, Okay. Dang it, $10. It's pretty good. So yeah, who asked this question? Vinay. I'm not even trying it by hand at first because this looks like a pretty, even integrating this simplified version is not easy. True, yeah. We can chop the bounds off this thing. Give Wolfram Alpha nowhere to hide. Oh my... What is this? It's like a horror movie if it was math themed. Oh my god. I see some complex variables in here. I think we should make Penn Center do this. So you really hate about the Bay Area too? That's fair. I grew up here. I went out of state for college and then I came back, and I don't want to spend my entire life here, but I generally like it. It was given as a homework, but I don't know how the hell to do it. It's apparently from a competition. That makes sense. Neon is saying this is the wrong method. I mean, I'd love to hear what the right method is. I see it. So exactly, Penbox. There's an I. It's Penn's problem. You know. I'll give this one a Google, but you may have just not been given a very fair problem to ask a student. Go from 0 to pi over 4 of. Even then, I think like I probably shouldn't be asking how much problems to students that are like this. If it's like an integration P problem. There's definitely be a solution. Check my Discord. Let's see. I might be able to do this differentiation in the integral sign trick. Oh, so we have to like Feynman's. Oh, wow. You know, Penn Center might actually be able to do this integral, but for a different reason, which is that 100 integral stream we did a while ago. King's rule? I remember him mentioning that. Let me drop the link to this image. Oh no, it's too long for the YouTube chat. All right, Vinay, I'll scroll through this and kind of show each part of it. It's definitely a competition type integral. You're using like King's rule and stuff. I probably... Oh my god, you have to start by doing 1/2 times 2 and bringing the 1/2 out front to give you... Actually, it's just easy. Never mind. I got extremely lucky with my apartment, Dr. Cook. And right now I'm unemployed, but I used to have a pretty decent paying job before I burnt out on it. So it's a combination of luck and at least previously having a good paying job. Okay, so the bounds do change to pi over 2 because of that u sub. Then what does King's rule give us? We just get a pi over 2 minus x for free for some reason. I assume there's reason for that, but some kind of symmetry there. And then you add this and this. Oh, you get rid of the x in the numerator? Wow. And then there's Queen's rule too? Oh my god, and you have to do a factoring trick with... You want it to be sine squared plus cosine squared squared, but you have to subtract off the extra term you get if you were to factor this out. Oh my god. California now is almost feudal? That's just not true. This is a difference of... Oh, they use the Pythagorean identity there. Sine squared plus cosine squared is 1, and 1 squared is 1. And then they do a half angle on sine x cosine x. There's also nothing wrong with not living in California too. I don't want to sound judgy. I probably already sounded judgy by what I said before, but people should live in a place that makes them happy. You know, that's the only thing that matters. They multiplied this through by secant squared over secant squared. Oh, so they can get another Pythagorean identity. But it doesn't quite line up with the Pythagorean identity because of that 2. So you say that minus tangent squared t is equal to minus 2 tangent squared t plus tangent squared t, and that's where this next line comes from. Yeah, there's no way in hell I can do this problem. Thank you for finding it, though, Neon. Transfer their non-zero property tax to their children or something? Oh, if there was, that's pretty fucked. I didn't hear about it though, but I don't follow it that closely. Okay, so I can at least I can upload this to Imager or something so you can have this image for yourself, Vinay. Let me do that quickly so you don't have to like go through the video of me scrolling through it. Because the link from Discord is a little bit too long to fit in YouTube chat. Crazyintegral.png. And I'll put the link to this image in the YouTube chat there. Oh, is that a link where you got that from? Let's look at that. Oh, okay, cool, cool. Thank you for just linking the source. So I'll just drop that link there. So yeah, I guess that's where Neon got it from. I'm sure there's, I don't know what Kings and Queen rule actually state, but there's a couple of tricks here that are very difficult to spot. That was in 1978? Wow. Yeah, thanks for coming for trying a question on me. I wasn't able to do it. We were able to get you an answer. Hmm. See, I do know that it doesn't get reassessed until it changes hands, but maybe there's an exception to that or something as well. See, I think I've learned about some of the consequences of this prop, but I didn't know that it came from this. Famous and influential ballot measure. Oh, that's good to know. Thanks for the information. Yeah. Anyway, what else did you send me? Try solving any one question. I don't think that's going to be possible for me. I'll bring it up and look at it, but yeah, I appreciate you like not going too deep into it. I really don't want to get like politics involved on the stream. Um, yeah, Neon, I don't even know how to begin on any of these questions, and I just don't enjoy doing this type of math. I'm sorry. Like I don't know. I just don't find these questions particularly even interesting to learn about usually. It's just a lot of algebra tricks and inflicting pain. This is a question paper for a 14-year-old. Better be a pretty smart 14-year-old. I'm not gonna get over how stupid this looks. You got 9 marks out of 100? Honestly, that's probably more marks than I would get. Okay, but before this, I was working on this relaxation method stuff, which I still want to do. So I was going to, I guess, start with this B right here. And we're going to set it to the average of the thing to the left, above it, to the right, and below it. Now, I assume it won't matter in the long run. But once I take the average and set it to be this B here, that's going to then influence when I go to this A and take the average of everything around it. And I think we're just going to let that happen. This feels like a nice moment for a function, right? So I don't have to think too hard about going one up, one down, one to the right. Do you want to plot stuff for Morn? I think you'd really benefit from getting access to Mathematica somehow. Go beg someone at Stanford. I'm doing this specifically with Python and NumPy because of that competition that I'm going to have with Zach. I need to relearn Python, and this just seemed like a nice opportunity to kill two birds with one stone. Because I've forgotten basically every coding language that I knew at one point, and Python seems like a natural thing to get back into it with. No, I think Zach is going to do some other language probably. I mean, he was saying he might handicap himself and choose a language he doesn't know, but... Oh, tell us your history? There's not much to tell. I feel like I haven't led a very interesting life. Oh. Well, the thing I'm doing on screen is, a coding problem from the E&M book, but it's practice for Zach and I are gonna do a little like coding competition on August 24th, I want to say. And so I don't remember how it came about, but I mean, if we can like make the format work for more people, it might be cool to get more, or to invite like you and others. I guess I would need to ask him about it, but yeah, we're planning to do a little coding competition. And Dr. Cook offered to make some problems for it as well. We talked about it on Zach's stream last week or something? Summer Slam down, yeah. So I've forgotten so much of my coding that it's a little bit sad, but over the next few weeks, I'm going to try and make more of an effort to remember it, because where I'm at right now is not good. It makes me really uncomfortable. Like when I specify the parameters, like I don't say their data type. And I kind of don't like that. Just like if you integrals for 48 hours on stream, no breaks. Oh god, it depends on the integrals. That does sound pretty terrible though. Okay. B11. Let's actually, oops. Let's do a little test here. Just let's make sure this is the expected. What? From 1 to 2. Like that. Is that average seriously 25? Oh my god, it is. It's 100 divided by 4. All right, see you, Neon. Thanks for hanging out. Does that 50 have a different average? 225. Okay, let's try it with that one. What? It shouldn't be 25. Oh wait, oops. I didn't change that one. 56. 56 times 4, 224. It truncated, but we shouldn't be truncating. There we go, 56.25. That seems... Yeah, that's right. Okay, so this is giving me the output that I expect, the little function that I wrote up there. We should do a little bit of, we should do some for loop action here though. So range, the first one is inclusive, the last one is exclusive. So if I want just 1 and 2, wait, no, we're doing the rows first. So the range is going to be from 1 to row 1, 2, 3, and we're going to stop there. So we want to go range 1 to 4, if I remember right. And then for J in range 1, 3 to get column 1 and 2. And that should update. No. These bad boys here. And we will do G separately, I think. Four? 0, 1, 2, 3, 4. This is going to be hard to do it for an arbitrarily large grid. And I shouldn't do it like this. I need to track how much I'm changing by. So, ugh. No. If np.abs c minus b I j is greater than change, then change equals that thing. Because we want the maximum change that we're doing. And then no matter what, we're going to set that thing to be C. I think that's what we want. Then at the very end here, we're going to print phi. Hey, stop adding extra lines. Is that good? I'm a little concerned that it's looping infinitely. I think it's looping infinitely. I need to do this thing, the same thing I need to do here for stop. This is not good. I feel like there should be a way better way to write this chunk of code, but this is what I wrote. What? Oh, okay, that's just the most recent. It's getting stuck at 12.5 for a change. You have to stand by your code. Unfortunately, I can't just copy code off your GitHub for everything. Well, I'm not calculating the change quite right. Because this isn't changing, but I'm getting 12.5 somehow. Unless, are any of these other ones changing? No, that they all seem to have like converged on a value here. I never reset change. Do I need to do that at the beginning of the loop? Or I guess at the end? Really? I would need to do that? Oh, it goes big and never settles down. Oh, yeah, okay. 2. Dang it. No, stop. Wait, no, that's, at the end. Don't look at me. Okay, wait, it still hates me. Why does it hate me? Oh, because, you gotta cool out change, you're causing a scene. You've changed, change. Yes, that's a good idea, Phobos. I got stuck on having to make the change to out here, but inside I wanted to be less than the possible. Okay. It's almost like you're really good at coding. Okay. So this seems reasonable. This is for 76. And since it's a separate problem, we can check the answer for 76 and not look at 77. Oh wait, there's a little bit more to this, to 76 though. They wanted to do this one by hand. I'm just not doing that by hand. Your final values on the array. Sketch the approximate course that two equal potentials been getting paid to go for about 19 years. Jeez. That two equal potentials for phi equals 25 and phi equals 50 have the actual continuous phi of xy. So, oh, I get what they want you to do. So they want you to kind of realize that the equipotential curve for phi equals 25, it's going to snake around. It has to be to the left of the 27. It has to be really close to this 25, and it has to be between the 18 and the 37, and then come up to the 25 and kind of, It does a kind of like looping thing. Like maybe it's better to show it in the books figure, I think. So, wait, where does it start? It starts at B. So we start at this B point here for phi equals 25. We come out here, wrap up and around here, touch back here, come here, and then we repeat the process as if this was our B. Okay. Oh, a heat map. Oh God. I have to do colors for that though. The wide-eyed Pikachu emote. Oh yeah, I that's probably on better TTV or something. The default heat map. Well, how do you do a heat map though? I never figured that part out. I don't think. Matplotlib heat map. Oh, that's right. I was trying to make the vectors be colors. Okay, let's do the import first. Where, just tell me which one is for the heat map. Is it I am dot sh or dot IM show? Plot dot subplots dot ax dot IM show. Let's see if we can do that all in one line. What did I just say? Plot dot subplot dot x. No. Oh, gold. Thank you very much for the raid. Welcome in, everyone. How's your stream? Been doing some it's a little bit of a slow part of the stream, so I've been trying to relearn some Python here. Yeah, but this is we're doing an E&M problem. It's called the relaxation method, which so far I guess it's been kind of relaxing, but you basically have an equipotential square in the middle, an equipotential square on the boundary, and at each of these points in the middle, you can just take the average of the points around it, and it actually converges on the solution. So he's been trying to code that up. You probably could do it recursively. I'm just doing it with loops. Making stats cake since I started the stats class. The hard with Excel? Oh no. So actually, this book wants you to do the first, they give you a simple version to do by hand, but I just wrote code to do it. and I'm trying to figure out how to make a heat map for it just because I think it'd be cool. Well, Phobos suggested it, but it would be cool. I was just trying to figure out how to recursively calculate stuff on the cells around it. Oh yeah, recursion. I am super rusty on coding, but recursion is one of the things I remember. Like even when I was good at coding, I wasn't that good with recursion. Daddy will be mad at me if those eyes look at any code other than Mathematica code. All right, and we're also at that stage where I'm just gonna shamelessly copy paste code. Blah, blah, blah. Yeah, I probably shouldn't copy paste it to the level of that though. ChatGPT is great for writing code. Oh, I'm not using ChatGPT. No AI. I'm doing the old-fashioned way, copying code off the internet. Yeah, Nibs are matplotlib here. Hey, Fizzbuzz, summoned. Oh, Phobos, you're on Team AI too? No, I can't get behind it. IDEs have AIs baked into them? Oh, God. I want AI to free me from the toil. Some by the word Mathematica. Welcome in, Fizzbuzz. Yeah, usually I go through phases where I enjoy coding, and then I realize how tedious it can feel a lot of the time. But I have a lot of motivation now because we're gonna have that competition with Zach. So it's important to know how to actually code. Yeah, but I don't know. I'm not using AI. Oh, if this is a spreadsheet solution for Laplace's equation. Wow. Your honor's at stake, coding for glory. If I don't do things the like arbitrarily harder way, how can I prove I really did them? If I arbitrarily the harder way, if I need the right code on the internet to copy and paste. I help design escape rooms. Every time my boss gives me pages of his code, I go to a dark place. That's sick though, you help design escape rooms. Okay. What? I am equals ax.im show. I'm not doing that. I'm not doing that either. I definitely want a tight layout though. Heaven forbid I have a loose layout. See, this is much better than using AI, let me tell you. Okay, we got something, and I can't easily show it on stream because of the way I have this IDE set up, but I'll put it into Paint. Actually, I about to say I want a bit more granularity in this heat map, but that's basically the next problem. So this heat map, it makes sense. It's about like what you would expect though, because it's pretty low like resolution. Like it's literally like 4 cells across, 6 cells down. No, but he can't spell his variable naming is like giving a toddler a book of matches. Oh no. We're seeing the average of the circle. Let's find the center property. Taking cells in the spreadsheet for. Oh, that makes sense. Maybe, yeah, it'd be hard to wrap to like, or it'd be a little bit weird to write, but that makes sense how a spreadsheet could be used there like that. Okay, so I'm going to claim that we've solved problem 76 and look at the answer. Because usually the answers, like, they do a really good job of adding some nuance that I didn't pick up on, even when I got to technically the right answer. No answers? No, I'm looking at for 76. 77 is the real coding one. I'm not going to look at that answer. But for 76, I think I did that. I didn't do it by hand, but I did it. And actually, oh no, that's what you mean by no answers. You're right. Ah, okay. I'm gonna say that I definitely got it right. That's I thought you were like judging me for looking at answers, but no, you meant like it's a problem, so there are no answers. I forgot. Dang it. Okay, well, I'm gonna assume that I picked up on all the nuance there then. No, I wonder if this works because B scales with 1 over r, not 1 over r squared. Like, that's the type of answer I'd be interested in hearing more about from the book on. Solve the infinite series and compare. I don't know how you would. Oh, I guess, yeah, Laplace's equation. But yeah, I guess the thing that I'm curious about this is why this averaging actually gets you to the right answer. It's another one of those things where it seems too simple. Like, it must be because of that 1 over, like, if it was 1 over r squared, I feel like it wouldn't be as simple as taking the average. Like, something would get messed up. Oh crap. I didn't even see the time. This stream is kind of flown by. Is Pen Center live? Maybe I should put a pin in problem 77. Oh, Pen Center is live. Yeah, I guess we'll cut things off there. I feel like we made some good progress here, though. Pretty happy that I just got an answer to 76 here. And next time I'm going to try to evolve this code to work for a finer mesh, which is what 77 asks. It's gonna. I'm just weird. I'm just weirded out by the indices. Well, it really shouldn't be that hard. I'm gonna try and save it for the stream, but I might get excited and do it off stream. We'll see. Because all you have to do is eliminate the first column and the last column, and then this one little corner. You deal with specially. Okay, yeah, let's call things there. So I'm gonna cut the YouTube stream off here. So if you're on YouTube, I appreciate you. I'm back on YouTube on Thursday. And goodbye, YouTube.